When astronomers traced 3i Atlas back through the stars, its trail didn't lead to another system, it led to nowhere. No star, no cluster, not even a background radiation. Just a void. Cold. Impossible. And then came the data anomaly, a faint repeating pulse hidden in its trajectory, pointing toward us. That was the moment one scientist whispered, "This thing didn't come from space as we know it." And suddenly, everything we understood about the universe began to unravel. Hello there, and welcome to the Sleepy Astronomer, a quiet place where impossible discoveries are told slowly, like stories the universe saves for those who listen long enough. If these calm journeys through mystery and wonder bring you peace, subscribing to the Sleepy Astronomer helps this constellation of curiosity grow, so more dreamers can rest beneath the same questioning sky. Tonight, we follow the trail of 3i Atlas, the interstellar visitor that shouldn't exist, whose origin defies every law we know. What is it? Where did it come from, and could it be carrying a message hidden in the silence of space? Take a deep breath and listen carefully. Because sometimes the universe doesn't need words to tell us that we've just discovered something we were never meant to find. This is the Sleepy Astronomer. The night is a soft mirror. Above you the stars shimmer with ancient patience, light that has travelled for millions of years, only to rest now upon your eyes. The air feels still, like the pause between breaths. In that stillness, you sense something moving far away, something vast, slow, and unbound by the rhythm of planets. It is not a satellite, nor a comet you know. It is older, colder, quieter. It is 3i/ATLAS, a visitor from the space between stars. You imagine it drifting at the edge of our solar system, sunlight touching its frozen surface for the first time in eternity. Each glimmer of light awakens fragments of dust, releasing whispers into the void. It is not alive, yet it tells a story, one written in gravity, ice, and distance. You close your eyes and listen, as if you could hear its motion, the faint hum of momentum continuing for millions of years, a lullaby of persistence. 3i/ATLAS is what astronomers call an interstellar object, meaning it does not belong here. It was not born from the same swirling disk that formed Earth and the Sun. Its origin lies elsewhere, in another star's long-forgotten nursery. Long before your world cooled, this fragment was cast out, a seed of rock and ice flung into infinite night. Imagine the violence of its birth, two worlds colliding or a sun's gravity tearing apart a forming planet. From that chaos, a traveller was born, set adrift without destination. For uncounted eons, it wandered. Between galaxies there are no roads, only silence. Stars appeared and disappeared in its distant view, each one too far to call home. It carried with it the record of time, molecules frozen in a structure untouched since the beginning of creation. Each atom within it remembers the universe's first fire, cooled into a patient calm. Now, by some delicate alignment of chance, it has entered the reach of human sight. You picture telescopes turning like faces toward the dark, instruments trembling at the edge of detection. A faint streak appears in the data, moving too fast, at too strange an angle, to belong to our sun's domain. At first, it seems like a mistake. But night after night, the movement continues. The path is real. Something from outside has arrived. You feel the quiet awe of the astronomers who first saw it. Their hearts beat faster, yet their voices stay low. Discovery often begins in silence, in the realization that what you're seeing should not be there. The object is named 3i/ATLAS, the third confirmed interstellar visitor, its name carrying both classification and myth. Atlas, after the telescope that found it, and fittingly after the titan who bore the heavens upon his shoulders. It seems the universe too has a sense of poetry. In your mind you follow 3i/ATLAS as it approaches the sun. Its orbit is open, not bound like the planets, not circular like comets. It curves once, then escapes forever. This is a one-time meeting, a crossing of paths between two cosmic wanderers. The sun's warmth begins to melt its surface, releasing gases that form a faint tail. That tail glows, not with fire, but with reflection, sunlight scattered through dust older than Earth. For a brief time it becomes visible to human eyes, a ghost written in light. You imagine standing under a night sky when 3I/ATLAS is there, faint but present. You can't see it without tools, yet knowing it exists changes the way you look upward. Somewhere in that vast blackness, a traveller from another system glides silently past your sun, a reminder that even the universe's stillness contains motion. You feel both small and deeply connected, as if you too are part of a great unending migration. The earth turns below you, cities sleeping, oceans breathing. Above it all, 3I/ATLAS moves undisturbed. It doesn't pause, doesn't look back. The gravity of the sun bends its path slightly, just enough to leave a curve in its story. That bend, gentle and precise, will never repeat. It is a signature, a single brushstroke in the universe's canvas. When it leaves, its trajectory will carry it into the outer dark, never to return. You think about what it means to visit only once, to appear, change what is known, and then vanish again. Perhaps every human life is a kind of interstellar passage, born from unknown origins, illuminated briefly, then continuing beyond sight. 3I/ATLAS becomes a mirror for that thought, drifting both outside and within you. Astronomers calculate its speed, nearly 60 kilometers per second, too fast for capture, too precise for chaos. Its path reveals no gravitational tether, no sign it was ever part of our solar family. It moves with freedom that planets can never have. Bound worlds orbit in repetition. Unbound travelers move toward forever. The idea fills you with both wonder and ache, the beauty of motion that knows no home. In this quiet, your thoughts slow to the rhythm of the stars. You sense how everything in the universe, even stillness, is part of a larger movement. Galaxies spin, atoms vibrate, hearts beat, comets drift. Nothing truly rests. Everything is carried forward by invisible tides. You realize you are part of that motion too, your breath synchronized with the pulse of existence. As 3I/ATLAS nears its closest point to the sun, its outer layers begin to sublimate, ice turning directly to vapor, no liquid stage in between. It's a delicate process, more like sighing than melting. In that vapor, fragments of ancient elements escape into space, tiny particles that may drift for millions of years, crossing orbits, perhaps falling someday into another world's sky. The traveller leaves traces, the way a story leaves echoes in the listener's heart. Soon it will fade from sight. The instruments will lose its signal, the data will thin to noise. Astronomers will continue to track its path through mathematics alone, predicting its outward drift until even numbers can no longer reach it. Yet for a brief moment, humanity and this ancient object have shared awareness, the knowing that something once invisible has entered our collective dream. You breathe deeply and picture it again, now moving away, shrinking into the black. There is comfort in its disappearance, not loss, but completion. Its purpose, perhaps, was only to remind you that the universe is wider than certainty, that even in a cosmos ruled by laws, there is room for wonder. The stars above seem slightly different now, not brighter, but more alive. You feel their distance not as separation, but as connection across vastness. Somewhere among them lies the birthplace of 3I/ATLAS, a cradle of rock and fire now unimaginable light years away. And as you gaze upward, you begin to wonder what stories lie hidden in that origin. What kind of place could send such a traveller into endless exile? The night grows quieter. The traveller drifts beyond the edge of perception. And in the silence it leaves behind, you sense a question forming, a question carried on light itself, waiting to be answered in the next glimmer of discovery. Light is always first to arrive. It moves faster than thought, faster than anything you can name. It travels not by permission, but by its own constant, a cosmic heartbeat that never falters. When astronomers first noticed 3I/ATLAS, they were not seeing the object itself. They were seeing sunlight, a reflection that had crossed millions of kilometers, bounced from frozen dust, and found its way to human eyes. You realize that even knowledge itself begins this way, a reflection, faint but faithful, of something real yet distant. You imagine a single photon leaving the sun. It bursts forth from the heart of fusion, hydrogen becoming helium, energy becoming radiance. The journey it takes is long and strange. For thousands of years, it bounces inside the sun's dense core before finally escaping outward into open space. And then, in the quiet of the solar system, that photon meets 3I/A TLAS. It touches the object's fractured surface, scatters, and continues onward until it reaches a telescope's mirror. That one photon becomes evidence, a whisper of light carrying truth across unimaginable distance. You close your eyes and feel that journey as a rhythm. Birth, reflection, discovery. It is the rhythm of all science. Curiosity as light, travel as time, understanding as return. The glow that revealed 3I/TLAS was not a shout but a whisper. It arrived as a fraction of brightness among countless stars, yet it was enough to signal that something beyond had crossed our path, enough to remind you that perception itself is fragile, built on the quietest of signals. Light is the storyteller of the cosmos. Every color, every wavelength holds information, temperature, motion, composition. When astronomers split the light from 3I/TLAS through a spectrograph, they were reading its autobiography. Each thin line of the spectrum marked the presence of an element. Oxygen, carbon, sodium, the same ingredients that once formed worlds. But there were hints too of something unusual. Ratios that did not match known comets. Subtle deviations, small but persistent, suggesting that this light had passed through matter, made in a different kind of star. You think about how light never lies, yet never explains itself fully. It offers evidence, not meaning. To interpret it, you must slow down and listen with patience. In that patience, you begin to sense the humility of observation, how fragile it is to draw certainty from radiance. And yet humans do it every night. They look upward, measuring brightness to understand time, distance, even destiny. The night sky becomes not a mystery, but a conversation between photons and the soul willing to receive them. You let that thought drift. Perhaps light is the universe's memory. Every beam that touches your skin began somewhere, from a star's furnace, from the reflection of a moon, from the scattering within Earth's own air. Each one a thread connecting moments across eons. The light that shows you the world today may have begun its journey before your species existed. When it reaches you, you become part of its story. The act of seeing is not passive, it is an exchange. You borrow a piece of the cosmos, and in return you offer awareness. In your mind's eye, you watch how light behaves near 3I/A TLAS. Some rays pass through thin streams of dust, bending as they go. Others strike the surface at shallow angles, revealing patches of ice untouched since before the sun was born. The reflected light is soft, diffuse, like moonlight through fog. It carries not just brightness, but texture, a sense of ancient quiet. You imagine that if silence had color, it would look like this. The telescopes on Earth and in orbit turn their gaze toward that faint signature. They capture frame after frame of data, faint dots flickering across time. Computers align those images, revealing motion where before there was only stillness. Each pixel becomes part of a cosmic map. To most, the image would seem like nothing, a grainy patterns of light and shadow. But to the astronomers, it is everything. It is confirmation that light has carried meaning faithfully across the void. You feel wonder at how something so vast can be known through something so small. The brightness recorded by their sensors is measured in fractions of a billionth of the sun's intensity. Yet those tiny measurements open doors to cosmic understanding. It reminds you that awareness often begins in subtlety, that revelation does not arrive in thunder, but in shimmer. Now you imagine being that photon again, racing outward and from 3I/ATLAS into the infinity of space. There are no roads, no barriers, only the endless dark. Yet even darkness is not empty. It hums with background light, relics of the Big Bang still echoing softly. Each particle of radiance becomes part of a grand continuum, connecting the first fire to the present moment. Through light, the universe remembers itself. On Earth, daylight fades. You sit in your quiet room, the faint glow of stars returning as the sun dips below the horizon. You understand now that even starlight is ancient, that what you see is not the present, but the past arriving late. The sky, then, is not a ceiling but a time machine. Every star is a message delayed by distance. When you look up, you're not simply observing the universe. You're witnessing history. And yet, as you consider 3I/ATLAS, you realize that its light tells not just a story of the past, but also a direction, a path forward. The way it shines reveals where it has been and where it is going. Its brightness increases as it nears the sun, then fades as it leaves. The pattern of that fading tells astronomers its speed, its shape, its surface. Light becomes both messenger and map, carrying within it the coordinates of the unknown. You take comfort in that even in the deepest dark, guidance exists. Light may weaken, but it never disappears entirely. It only travels farther, slower, scattering into infinity, waiting to be found again by eyes that know how to see. You imagine those photons continuing long after humanity itself has changed, still travelling, still telling their story to whoever may come next. As the last reflections of 3I/ATLAS's light leave your imagination, you sense a question forming quietly in your chest. If light can tell us where a thing has been, can it also reveal where it came from? Can the patterns within those ancient rays trace back to an origin older than stars themselves? The question glows softly, like a star rising behind thought, and you find yourself turning toward those who first looked deeper, toward the astronomers who followed the light to its impossible beginning. The observatories never truly sleep. Inside their domes, the air hums with quiet electricity, the pulse of machines tuned to the rhythm of the stars. You picture the astronomers there, faces pale in monitor light, eyes reflecting distant suns. Outside, night stretches vast and unmoving, but inside everything is alive with motion. A line of data updates, a telescope shifts a fraction of a degree, and the universe reveals a little more of itself. You sit among them in thought, breathing their stillness. They are not heroes of adventure, but keepers of patience. Each night they return to the same small portion of sky, measuring, comparing, aligning. Their hands move with care, adjusting lenses, correcting exposure, refining focus until the signal sharpens. The work is quiet, almost meditative. Every observation feels like a prayer to the unknown. When 3I/ATLAS first appeared, it came not as spectacle, but as anomaly. A faint, misplaced glimmer on a digital frame. One astronomer noticed its speed and too quick to belong to the familiar family of comets and asteroids. Another confirmed that its orbit was not closed. The discovery spread through emails written in hushed excitement, filled with numbers that hinted at something extraordinary. You imagine their hearts racing as they realized what it meant. This object was not of our system. It came from elsewhere, from interstellar space. For most of them, the word interstellar had existed only in equations or dreams. Now, it had found form, a trace of something beyond human origin, visible, measurable, real. They began to track it relentlessly. Night after night, they gathered data measuring the faint movement of light against a background of stars. Each observation added another point, another clue. The orbit they mapped curved backward, tracing a line that stretched far beyond the edge of the solar system, beyond even the outermost comets. It pointed toward a region of space so empty, so quiet, that it seemed to belong to nothing at all. The astronomers argued softly, their discussions filled with care. Could this be a remnant of another star's birth? A fragment ejected from a distant system? Some thought it might have passed near other stars before entering ours, guided by gravitational threads too faint to follow. Others wondered if it had drifted freely for billions of years, untouched since the dawn of galaxies. The questions multiplied, not in chaos, but in awe. You picture one astronomer, alone, long after midnight, staring at the data. Outside, the wind moves gently against the dome. Inside, she watches a curve on her screen, a line representing motion through space and time. It is beautiful in its simplicity, this quiet mark of the unknown. She imagines following it backward, like a river toward its source. Where does it lead? What kind of place gives birth to such a traveller? In that moment, science becomes not just calculation, but listening. Every number, every pixel of light is a whisper from something vast. To truly understand, she must silence her own expectations, letting the data speak in its own language. You realize how delicate that act is, the art of looking without assumption, of letting mystery remain long enough to reveal itself. The astronomer's tools are many: telescopes across continents, orbiting observatories, computers filled with models of gravity and time. Yet none of it would mean anything without the curiosity that binds them. Curiosity, that ancient impulse that once lifted human eyes from firelight to starlight. You feel it stirring in you too, as though the same question lives in every mind that dares to look up. They run simulations, rewinding the motion of 3I/ATLAS across thousands, then millions of years. In digital form, the object travels backward through the solar system, past Neptune, past Pluto's faint path, until it crosses the threshold of interstellar space. Beyond that, the models begin to fail. Small uncertainties in data become wide rivers of possibility. Each recalculation yields a slightly different origin, a scatter of potential birthplaces spread across the galactic map. Still, one pattern stands out. The trajectory points toward a region between constellations Lyra and Hercules. Not toward any particular star, but into a void between them. It is a direction, not a destination. The astronomers grow quiet. It is as if the object has come from nowhere, from a silence within the structure of the Milky Way itself. You sense their humility in that realization. The universe, once mapped in confidence, suddenly feels immeasurable again. 3I/ATLAS becomes a reminder that knowledge is not an ending, but a horizon, one that moves as you approach. Every answer deepens the question it was meant to close. In one of their meetings, an older astronomer speaks softly. "Perhaps," he says, "we are not meant to find where it came from. Perhaps what matters is that it came at all." The room falls silent. They understand science is not only about certainty, it is also about wonder, the courage to dwell in not knowing. You breathe slowly, feeling that same quiet understanding. To look up is not merely to measure, but to remember your place in something larger. These astronomers, with their equations and patience, are translators between the infinite and the human. Through their eyes, you too become part of the search. The data continues to refine. The orbit sharpens, parameters adjust, but each improvement only deepens the mystery. The backward path of 3I/ATLAS does not lead to a known star, nor even to a region dense with matter. It comes from the outskirts of the possible, a space so sparse that physics itself seems to hesitate there. The astronomers begin to call it simply the origin region, a name that admits both knowledge and ignorance. Outside their observatories, dawn approaches. The first light of morning creeps across mountaintops, reminding them that their work belongs to the same sunlight that reveals 3I/ATLAS. One by one, they shut down their instruments, saving files, logging observations, whispering quiet goodnights to the stars. You watch them step outside, blinking against the soft brightness of day. Their faces are tired, but their eyes still carry starlight. You feel their devotion, not to answers, but to the act of looking, to seek, to measure, to wonder. That is their way of belonging. As you drift in their shared stillness, you sense that the story of 3I/ATLAS has only begun. Its light revealed its presence, its motion revealed its strangeness. But what lies behind that motion, what force, what history, what improbable shape, still waits in shadow. And somewhere, beyond equations and screens, a question begins to rise like a faint new dawn. If its orbit breaks every pattern, then what truly is its form? It drifts against the velvet dark, a shard of something older than the sun. Through telescopes, its body appears faint, but its shape refuses comfort, too elongated, too uneven, too restless to be ordinary. You feel a strange pull, as though the object itself resists being seen. It rolls, tumbles, hesitates, not in the smooth arcs of known comets, but in broken rhythms, as if remembering how to move. Astronomers call it non-gravitational acceleration. A polite phrase for behavior that shouldn't happen. It moves as if nudged by invisible fingers. Yet there are no jets of gas, no outbursts of ice turning to vapor. The sun warms it, but nothing escapes. It simply changes direction quietly, defiantly, so as though it knows another way to travel. You imagine it not as rock, but as thought, a geometry of memory adrift through silence. Its surface is scarred, fractured into facets that catch faint sunlight. When light hits, it flashes in unpredictable ways like the glint of water under moonlight. It turns light into language, and you try to listen. Perhaps you think the shape of a thing carries the story of its birth. Mountains are born from pressure, rivers from gravity's persistence, and comets from frozen time. But this one, 3I/ATLAS, feels different. Too long, too thin, as though stretched by forces unfamiliar to your solar imagination. Its ratios defy the patterns you've learned from centuries of observing other travelers. It seems carved by something that works slower than time itself. The astronomers model its rotation, their computers sketching paths and probabilities. Yet no simulation remains stable. Every outcome collapses after a few hours of motion. It refuses prediction. It reminds you of dreams, how they make sense only while you're inside them. Its spin, they say, is tumbling, chaotic rotation not aligned with any single axis. Imagine a leaf in water caught between currents. It never repeats a motion exactly. One turn is sharp, another soft, another unpredictable. Each spin erases the one before, yet together they create something that feels oddly deliberate. Perhaps chaos, when stretched long enough, begins to look like purpose. You close your eyes and picture it moving, a shard of twilight, twisting endlessly, carrying frost that predates Earth. It does not shine like stars or planets. It glows faintly, like memory reflected on still water. In that dim light, science and wonder blur. Every measurement feels like a question whispered into darkness. Dust trails follow comets, normally, delicate veils of evaporation painting arcs behind them. But this one leaves nothing ordinary. Its trail behaves like static in space, forming patterns that shift, dissolve, reform. Dust that refuses to fall in line. You imagine that every particle remembers a different version of home. Perhaps the cosmos keeps secrets not through hiding, but through excess, through too much truth to fit inside human comprehension. The data piles up, but patterns slip through like sand between fingers. Still, astronomers keep looking, adjusting their telescopes, refining models, arguing quietly across the hum of servers. Some say it's a fragment of a shattered world, torn apart by tidal forces near a star. Others whisper it might be a relic from the earliest dust, the kind that once drifted before galaxies even had names. You sit with both possibilities, feeling how each carries its own kind of beauty. The universe, after all, does not choose between poetry and physics. You think about shape itself, how it defines and confines. Every planet is a compromise between motion and pull, between wanting to stay and needing to move. But this traveller has broken that symmetry. Its body does not yield to spherical comfort. It carries defiance in form, like a signature left by some forgotten craftsman of the cosmos. Maybe the shape is not an accident. Maybe it remembers where it came from, a region where gravity whispers differently, where matter learns another rhythm. You imagine it passing through fields of charged dust, sculpted slowly by unseen tides. Its surface could be a palimpsest, ancient collisions, frozen flows, cosmic graffiti written in ice and silence. Even now, as it moves through the sun's light, the object remains cold. That is the most mysterious part. The warmth that melts other comets merely brushes against its skin. It absorbs nothing. It reflects, resists, and glides away. There is a lesson here, you think, about distance, resilience, and the power of remaining unchanged even in the presence of immense light. You picture the astronomers late at night, watching data scroll across screens. The numbers are dry, but behind them hums a quiet astonishment. No one says it loud, but all feel it. This object should not exist as it is. Yet there it is, silent, spinning, indifferent to our equations. Science becomes, for a moment, a meditation, a way of listening to what refuses to explain itself. You wonder how many other impossibilities drift unseen beyond the sun's reach. How many shapes would we call impossible simply because we have not met them yet? The universe seems to be teaching humility, showing that even the smallest fragment can expand the boundaries of what real means. It drifts farther now, beyond Mars, beyond Jupiter, heading back into night. Its shape remains unyielding, strange, unforgettable. You imagine it moving still, carving a path through interstellar dark, a reminder that form is only another kind of language, one that space itself speaks fluently. And as it fades from the reach of our telescopes, you feel a soft question rise within you, one that glows as faintly as the comet's reflected light. If something so strange can exist, what other patterns of the universe remain unseen, waiting, patient, just beyond the curve of our understanding? The question lingers, unhurried, guiding you gently toward the next thought, toward the mathematics of memory. You sit in the quiet hum of an observatory, surrounded by the soft pulse of machines. On the screens before you, numbers cascade like rain, not random but ordered, deliberate, endless. Each digit hums with purpose, translating motion into meaning. The astronomers speak gently to one another, not in sentences but in variables. Their language is made of light, speed, and uncertainty. They are trying to remember something, not with their minds but with mathematics. Equations, they say, are a kind of memory. Each one holds a story the universe once told. The orbit of a planet is the memory of gravity's first invitation. The arc of a comet is the recollection of a collision long forgotten. Even 3I/ATLAS, that fractured wanderer, is following the faint script of a force that touched it billions of years ago. You watch as a scientist adjusts a curve on the screen. The line bends ever so slightly, then stabilizes. The motion of 3I/ATLAS begins to fit the model, but not completely. There's always something left over, a residue of difference, a remainder that refuses to vanish. In mathematics, that remainder is called error. In life, you think, it's called mystery. Each equation they build tries to bring the impossible into order. They chart the object's path backward in time, using coordinates and gravitational influence. The formulae stretch across the solar system, pulling on every planet's mass, every photon's pressure, every invisible thread of attraction. The universe, after all, is a web of relationship, a conversation between things that can never touch yet always influence. Numbers begin to resemble constellations. You imagine connecting them with the lines of thought, like stars linked by ancient storytellers into meaning. The variables become celestial. G for gravity, V for velocity, M for mass. But behind each letter hides emotion. Gravity feels like longing. Velocity feels like freedom. Mass feels like memory. The universe's way of saying I was here once and I still am. The astronomers run simulations again and again, changing assumptions, refining margins. No matter what they adjust, a small deviation remains. The path of 3I/ATLAS does not fully obey Newton's tidy universe. It moves as though it remembers something we cannot measure, a gentle insistence against total explanation. You begin to understand that mathematics too has edges. Beyond those edges lives everything we have not yet learned to name. A scientist nearby murmurs about perturbation, how distant bodies tug ever so slightly, shifting an orbit by a fraction of a fraction. It's beautiful, you think, that even gravity's smallest whisper can echo across light years. Perhaps memory works that way too. The smallest experience, a glance, a sound, a falling star, can alter the orbit of a life forever. The equations grow more intricate. Differential calculus weaves through orbital mechanics. Tiny forces become infinite loops. Every variable leads to another unknown. It feels less like solving and more like listening. Mathematics is no longer a cage for understanding, but a rhythm, a song written in symbols. You remember something one of the astronomers once said, "Mathematics is how the universe dreams itself." You let the phrase settle. Dreams are never precise, yet somehow true. Maybe that's why these equations, elegant and unyielding, always leave room for awe. Outside, the night is clear. Stars blink like patient data points waiting to be interpreted. You step out into the cold air, letting the quiet of the cosmos wash over you. Above, the same laws being computed inside the observatory are unfolding in perfect silence. Planets curve in obedience to invisible geometry. Moons sway in resonance. Space expands with a precision too vast for comprehension. You breathe deeply, feeling numbers in your chest, a strange comfort in their certainty. Even chaos, you realize, has pattern. Even randomness hides symmetry. And memory, whether of a human or a comet, is simply motion repeating itself in a slightly different way each time. Back inside, the models are now tracing the comet's journey not only through space, but through time. They run the simulation backward, minute by minute, year by year, century by century. As they do, 3I/TLAS seems to drift away from the Sun, past the frozen outskirts of the solar system into the interstellar gulf. Every recalculation erases part of our known universe from the map. The numbers begin to point towards somewhere else, a direction with no familiar stars. And yet, the equations hold, they keep whispering, keep translating. One of the astronomers writes a note in the margin of a graph, trajectory stable beyond expected limit. It's a quiet phrase, but everyone feels its weight. The data implies that 3I/ATLAS did not just wander in by chance. Its motion carries memory, coherence, as though something placed it into that path long ago. You imagine memory as gravity's twin, an invisible force pulling events together across time. Perhaps the universe keeps its memories not in words, but in trajectories. Every orbit, every spin, every photon of light is a story the cosmos refuses to forget. The scientists discuss uncertainties, the tolerance of measurement, the precision of their instruments. You watch their faces glow in the light of their screens. Beneath their calm professionalism hums something ancient, wonder. The wonder of realizing that the universe is not only vast, but aware, not conscious in a human sense, but attentive. It remembers every motion, every decay, every spark of creation. Nothing is ever truly lost, only transformed into another form of record. And perhaps that is why 3I/ATLAS resists the neatness of equations. Maybe it carries a memory older than our physical constants, the remnants of forces that shaped matter before our universe had cooled. You think of it as a witness, a drifting archive written in the language of dust and trajectory. In the stillness, you sense the boundary between mathematics and meditation fade. Each formula becomes a breath, each solution a pause. You find yourself counting not numbers, but moments, each one precise, finite, and infinite all at once. The night deepens, data continues to gather, patient and tireless. Somewhere between the zeros and ones, something alive stirs, not biological, but meaningful. It is as though the universe is teaching you to listen with numbers, to see patterns not as answers, but as invitations. The astronomers know they may never fully decode the path, still they continue, not out of certainty but devotion. Their equations stretch outward like prayer flags in the wind, each one a gesture toward understanding, fluttering against the unknown. You realize then that mathematics is not just calculation. It is remembrance. It is the art of writing eternity into the language of change. And as you watch the comet's path fade into the simulation's distant horizon, a quiet thought settles in your mind. If mathematics is memory, then perhaps velocity, the way something moves, is emotion. And if that is true, then what emotion sent 3I/ATLAS here? The question lingers like starlight that refuses to fade, guiding you softly toward the next mystery, the whisper of velocity. You focus now on speed, the purest form of motion, stripped of noise and decoration. 3I/ATLAS moves faster than any natural object that belongs to the solar system. Its velocity is the first clue that it is not from here. Most comets orbit the Sun at predictable speeds. They come from the Kuiper belt or the Oort cloud, bound loosely by the Sun's gravity. But this one came in fast and leaves faster, too fast to ever return. Astronomers measure its velocity carefully. Every number matters. They calculate how sunlight pushes on it, how gravity bends its path, how small outgassing might change direction. After accounting for all forces, one factor remains constant. 3I/ATLAS entered our solar system already moving faster than the Sun's pull could slow it down. Its hyperbolic trajectory proves it. The object is interstellar. You imagine its journey through space, millions of years moving between stars. Out there is no resistance, no friction, no sound. Motion never fades. Once set in motion, an object continues until something interrupts it. That is what velocity means in space. Persistence. The same movement for as long as time allows. Velocity is not just speed, it is speed with direction. That difference matters. A comet's orbit curves, meaning its velocity changes constantly as it bends toward or away from the Sun. But 3I/TLAS does not orbit. It follows a single path, bent only once by gravity, then continues into infinity. It does not circle back, it does not belong. It passes through, untouched except for the brief influence of our system's mass. The numbers describing its motion are simple yet astonishing. It entered the solar system moving at about 30 kilometers per second relative to the Sun, nearly 108,000 kilometers per hour. As it left, it was still moving nearly the same speed. That is faster than any probe launched by humans so far. It crossed the distance between planets in weeks, not months. By the time telescopes located it, it was already leaving. Speed shapes everything about this object. It determines how it looks, how it behaves, how long we can study it. The faster something moves, the shorter the time we have to observe it. The comet gave scientists only a small window to collect data. Every night mattered. Every observation had to be precise. By the time equipment was calibrated and telescopes aligned, it was already fainter, already farther away. You think about how speed affects perception. When something moves too fast, it becomes invisible. Our eyes cannot follow. Our instruments struggle to lock on. The same happens in life. The faster things move, the less we can understand them while they pass. 3I/TLAS reminds scientists of that truth. Its velocity makes it free but also unknowable. Astronomers use velocity to learn origin. In physics, speed is a signature of history. How fast an object moves tells you where it might have been born. Every star, planet, and comet in the galaxy moves within certain limits. But when something exceeds those limits, it tells a story that began elsewhere. 3I/TLAS might have been pushed out from another star's system, perhaps during a planet's formation or a stellar encounter. When massive bodies interact, gravity can fling small objects into space, accelerating them beyond escape velocity. Once released, they drift through the interstellar medium, carrying their speed like a record of that event. That is likely what happened here. Billions of years ago, near a distant star, gravitational interactions could have launched it into space. For countless ages, it travelled between systems, its motion undisturbed. Space between stars is nearly empty, only a few atoms per cubic centimetre. With nothing to slow it down, the comet maintained almost the same velocity until it reached ours. In that way, velocity is a kind of memory too, a preserved state. The object's speed today is the same speed it has carried for ages. It has not forgotten its beginning. Even though it has crossed unimaginable distances, its movement remains steady. That constancy is comforting. In a universe full of change, velocity can be permanence. Astronomers compare it to 1I/Oumuamua, the first confirmed interstellar object discovered in 2017. Oumuamua was also fast, also on a hyperbolic path, also unlike any known comet. 3I/TLAS behaves differently, but the shared feature is speed. Interstellar visitors seem to arrive with the same unstoppable momentum. Each one reminds us that the galaxy is not empty. It is alive with travellers, each carrying its own story written in motion. Velocity connects everything. Earth moves around the Sun at about 30 kilometers per second. The Sun itself moves around the Milky Way's centre at roughly 220 kilometers per second. Even while standing still, you are moving through space at unimaginable speed. You are part of the same flow, a participant in the same constant motion that carries comets, planets, and stars. The scientists use Doppler measurements to confirm direction. Light shifts slightly depending on motion, blue when approaching, red when receding. The colour of reflected sunlight from 3I/TLAS shows that it is already receding, moving away. Each measurement becomes a farewell note. Once its light shifts beyond detection, the object will disappear completely from our reach. Velocity in the universe has no noise, no wind, no feeling of motion. Objects move endlessly through silence. That is the paradox, immense speed within complete stillness. In space, you cannot feel velocity. You only see its effects. The blur of stars, the changing positions, the slow fade of a traveller leaving behind nothing but trajectory. You wonder if speed and solitude are connected. The faster something moves, the less time it spends near others. 3I/ATLAS, in its rapid passage, interacts only briefly with worlds. It does not stay long enough to gather dust or to be captured by gravity. Freedom in its purest form seems lonely. As the data continues to come in, one pattern stands out. Its motion is precise but not random. Every angle, every deviation follows physics exactly. Yet beneath those calculations lies something deeper, a sense of direction that feels deliberate. Perhaps not chosen, but anciently assigned. The universe does not give meaning, but it gives motion. Motion becomes its own form of meaning. When astronomers plot its future path, it points outward, back into interstellar space. It will travel into darkness again, unseen and unmeasured, carrying the same silent speed. In another star system, millions of years from now, it might pass close enough for someone else to detect. And they will ask the same question we ask now. Where did it come from? Speed hides answers as much as it reveals them. It shows that something moved, but not always why. Velocity is the evidence of cause, not the cause itself. And as 3I/TLAS fades beyond telescopes, its whisper of motion remains, a reminder that movement alone can hold a kind of truth. You think of it one last time. A small cold fragment moving faster than comprehension. Not rushing, not fleeing, just continuing. The universe moves with it, as it always has, and you begin to wonder, if velocity remembers where it began, then what does the cold remember? The next question waits quietly beyond the edge of heat, in the cold that holds all things. You move outward, away from the inner planets, away from the familiar glow of the sun. The light fades behind you, not suddenly but gradually, like a dimmer switch lowering across time itself. Temperature drops slowly at first, then rapidly, until numbers fall below anything you have felt before. In this place, cold is not a passing sensation. It is the background condition of existence. Beyond Neptune, beyond the Kuiper belt, the solar wind weakens. There are fewer particles here, fewer collisions, fewer sounds. Space becomes almost perfectly still. What remains is a form of emptiness that is not dead but deeply calm. The thermometer reads only a few degrees above absolute zero, the point where atomic motion nearly stops. Yet even here, movement continues. Too subtle to see, but never gone. 3I/ATLAS passes through this realm with silent purpose. It does not slow, for there is nothing to slow it. The object carries with it a temperature of its own, the thermal memory of its birthplace. Instruments aboard distant telescopes read the faint infrared signal that escapes from its frozen surface. The data shows that it is colder than any natural body found near the Sun, colder even than Pluto's shadowed craters. Its temperature hovers near 30 kelvins, about minus 243 degrees Celsius. At this point, chemical reactions are nearly impossible. Molecules freeze into stillness, yet still, the object moves. In this outer darkness, the meaning of cold changes. On Earth, cold means discomfort, shivering, survival. Out here, cold is structure. It defines the shape of matter. It allows fragile ices to remain solid for billions of years. It protects molecules from breaking apart. It preserves memory in the language of chemistry. The water locked inside this object may have existed since before the sun formed. It has never melted, never boiled, never moved, except now as it crosses your system once and never again. Telescopes try to track it, but the signals are faint. Light takes hours to reach us from its current distance. The reflection is weaker than expected, suggesting that its surface absorbs rather than scatters sunlight. Some researchers speculate that a layer of dark organic compounds coats it, carbon chains formed in the interstellar medium hardened by the radiation and time. These coatings are common on long-traveled bodies. They absorb visible light, turning the object almost invisible. It glows only in the infrared, like a whisper of warmth in an ocean of cold. Cold also affects time, or at least how we measure it. Atomic clocks, those devices that define the second, rely on the vibration of atoms. At near absolute zero, vibrations slow, frequencies shift, and precision increases. In deep space, time feels stretched, as though seconds take their time to unfold. You imagine 3I/ATLAS carrying its own clock, one defined not by human machinery, but by the stability of atoms that barely move. The absence of heat means the absence of chaos. Without motion, entropy slows. Systems stop changing quickly. What you observe is a kind of pause in the universe's constant activity. The interstellar medium here is not empty. It is just extremely quiet. A few stray hydrogen atoms drift past each cubic centimetre, each moving at a few kilometres per second. Their collisions are rare, their exchanges infrequent. Still, those faint interactions add up over millions of years. Cold does not mean nothing happens. It means that everything happens very, very slowly. Scientists studying 3I/ATLAS use this cold as a laboratory. They compare its surface chemistry to that of comets from our own system. They analyse how certain compounds survive radiation when frozen at such temperatures. They discover that cosmic rays create simple molecules like formaldehyde and methanol even in near-vacuum conditions. These small molecules can later form amino acids and sugars, the building blocks of life. Paradoxically, the cold that stops motion also allows creation. It preserves, accumulates, and waits. As you continue to imagine this journey outward, you begin to realize that temperature is a kind of storyteller. Warmth tells the story of activity, of reactions, combustion, metabolism. Cold tells the story of endurance. It records what has lasted. 3I/ATLAS carries that story like an archive, every frozen atom a word from a time before the sun. In this cold, you notice how silence has a texture. It is not blank. It feels layered, thin, soft, endless. Radio telescopes tuned to this region pick up the faint microwave background radiation, the afterglow of the Big Bang. Even here, energy from the universe's first light still passes through. The temperature of that radiation is about 2.7 kelvins, almost absolute zero, but not quite. It is the baseline temperature of the cosmos, the cold that holds all things. Every object, every planet, every particle rests within that same faint warmth, a reminder that even emptiness glows faintly with history. You picture atoms at this temperature. Hydrogen atoms spin so slowly that their internal energy levels change only once every million years. Helium remains inert, refusing to bond. Oxygen and carbon form ices that never sublimate. The laws of physics continue to operate, but at a glacial rhythm. If you could stand here, you would hear nothing, feel nothing, and yet everything around you would be alive in its own slow way. Astronomers describe this region as part of the heliopause and beyond, the boundary where the solar wind gives way to the interstellar medium. It is a transition zone, a place where pressure balances and the sun's influence fades. Beyond it lies the true interstellar environment, the domain between stars. For 3I/ATLAS, crossing this region marks a return to its natural habitat. The object was never bound to the sun's gravity for long. Its hyperbolic trajectory ensures escape. Once it passes beyond this boundary, it will continue moving through interstellar space indefinitely, unanchored, undisturbed. The spacecraft Voyager 1 and Voyager 2 also travel in this region, though they move much slower. Their instruments record similar conditions, temperatures near absolute zero, near vacuum pressure, and radiation levels that speak of cosmic rays rather than solar particles. Voyager's sensors detect the plasma waves of the interstellar medium, a faint hum that proves space is not silent but simply very quiet. Somewhere, 3I/ATLAS glides through that same hum, unaffected, indifferent, eternal. What you feel as you consider all this is not fear or isolation, but a sense of perspective. The cold is not against life, it is the canvas upon which life happens. Without cold, heat would have no meaning. Without stillness, motion would have no contrast. The extremes define the middle. In that balance lies everything we know. You imagine that if you could follow 3I/ATLAS further, you would see how the cold sculpts the shape of galaxies themselves. Interstellar dust clouds collapse only when they radiate away heat, cooling enough to allow gravity to take hold. Stars are born from cold. Even the sun began in a pocket of darkness where temperature fell low enough for hydrogen atoms to cling together. From cold came warmth, from stillness came motion, from silence came light. As you drift with the object in thought, you sense that the universe does not waste anything but time. Not energy, not matter, not even cold. Everything serves a purpose in the vast system of balance. The cold that holds all things is the same cold that preserves possibilities. Without it, the universe would burn out too quickly, every reaction exhausting itself in moments. Because of cold, time stretches. Because of cold, the story continues. You let that realization settle. The stars are far away, the sun is a distant point, and yet you are still part of this balance. The warmth of your body, the heat of thought itself, exists only because somewhere else there is cold. Every spark of warmth needs a background of stillness to be seen. Every question needs silence to echo against. As you look beyond, you sense that the next step in understanding 3I/ATLAS will not come from observing its present position, but from tracing its past. To know where it comes from, scientists will rewind its path through the mathematics of motion, following it back through space and time. Somewhere in that rewind, another mystery waits, one that may lead beyond the known boundaries of the galaxy itself. And as you think of that, you realize that the cold is not the end of the story. It is only the beginning of the trail backward through time. When an object leaves the solar system, it doesn't just disappear. It leaves behind a trace, a measurable pattern in the sky, a sequence of coordinates that describe its path through space. For 3I/ATLAS, that trace became an obsession for astronomers. They wanted to know where it came from, not just where it was going. The problem was that its path made little sense. It didn't match the orbit of any known comet, asteroid, or interstellar fragment. So they began to rewind it, to follow the trail backward through time. Tracking something across interstellar space is not simple. The data begins with observation, a few bright points recorded over several nights. From these, computers calculate its orbital elements: speed, inclination, eccentricity. 3I/ATLAS moved fast. Almost too fast to belong to the sun. Its trajectory was hyperbolic, meaning it wasn't captured by a solar gravity. It was only passing through. By running these orbital calculations in reverse, astronomers could simulate where it might have been before entering our system. To a line of code rewound the clock, step by step, millions of years into the past. The further back they went, the more uncertain the path became. Tiny measurement errors, a few fractions of a degree, turned into massive deviations over long timescales. Gravity from planets, radiation pressure from sunlight, and even the pull of distant stars all influenced the object's motion. To account for this, these scientists built complex models. They factored in every known gravitational source within 100 light-years. They included the subtle drag caused by interstellar gas. They even simulated the influence of passing stars whose gravity could have nudged the object from its origin. Each new model changed the story slightly. In one simulation, the object came from near the constellation Lyra. In another, it emerged from deep within the Scorpio-Centaurus region. The results varied, but one theme remained. Its origin lay far beyond the boundaries of our local interstellar neighborhood. It had been traveling for millions, perhaps hundreds of millions, of years. Whatever event sent it on this path happened long before humans existed, possibly before Earth's continents had even taken their present shape. What made 3I/ATLAS special wasn't just its speed or shape. It was the fact that it carried direction, evidence of a single journey from an identifiable region of space. Interstellar dust doesn't travel like that. It disperses. It spreads evenly across the void. But this object had a clear vector. It was a messenger, not debris. That made astronomers wonder whether it was a remnant of something larger, perhaps a planetary fragment ejected from a young star system, or the frozen core of a long-dead comet expelled by the gravitational chaos. To find its likely source, researchers cross-referenced its path with catalogues of nearby stellar motions. Every star moves relative to every other, orbiting the galactic center at different speeds and directions. By tracing both the objects and the star's movements backward in time, they looked for intersections, moments when 3Arni/A, T, LAS might have passed near a particular system. If such a crossing occurred, it might indicate where the object was thrown from. After countless calculations, one possibility emerged. Several models placed its trajectory within a few light years of a small dim star about 40 million years ago. The star was unremarkable, a red dwarf, one of hundreds of billions in the Milky Way. Yet its proximity to 3A/A, TLAS's reconstructed path could not be ignored. Perhaps, long ago, a planet or icy body orbiting that star was perturbed by another passing star. The gravitational encounter could have flung fragments outward, ejecting them into interstellar space. One of those fragments might be what we now call 3I/ATLAS. But even this theory felt incomplete. The more the data was refined, the more it seemed that the object's path extended beyond the reliability of any model. There came a point when calculations entered regions of space, unconnected to known star systems. The path didn't simply fade, it bent in ways that didn't align with galactic dynamics. A small but consistent deviation appeared in all the most accurate simulations. It was as if the object's trajectory curved around something unseen, a gravitational influence that current models could not explain. That anomaly caused debate among researchers. Some said it was simply numerical error, a rounding problem magnified across time. Others suspected something deeper, an unseen mass, perhaps a dark object, influencing motion without light. The idea of a hidden gravitational field, a cold, non-luminous structure, reignited discussions about dark matter in the local galactic region. Could 3A/ATLAS have interacted with a cluster of dark matter before entering our part of the galaxy? If so, its path could be evidence of something humanity has never directly observed. To verify, astronomers turned to data from space-based observatories. They checked for gravitational microlensing events, small distortions of light from distant stars caused by invisible masses. Some regions along the backward traced path showed unusual lensing signatures, nothing conclusive, but enough to raise questions. The universe, they realized, still held structures too faint to map, too large to ignore. Meanwhile, the physical data from the object continued to arrive. Spectroscopic readings, color indices, and albedo values gave clues about its composition. Some scientists began to compare these properties with known interstellar dust from different galactic environments. The chemistry didn't match our region. Ratios of isotopes, particularly oxygen 18 to oxygen 16, were distinct. It was not from any system near ours. Its atoms belonged to an older region of the Milky Way, possibly formed in a molecular cloud billions of years before our Sun existed. The more they studied it, the older it seemed. Its isotopic ratio suggested formation during an earlier cycle of stellar birth and death, when massive stars lived short, violent lives and seeded space with heavy elements. That meant 3I/ATLAS might not just be older than Earth, but older than the Sun's entire generation of stars. The object was a fossil drifting between epochs. As the models projected farther backward, something strange emerged. Around 50 million years into its simulated past, the equations began to behave unpredictably. The object's trajectory appeared to converge toward a coordinate point outside the galactic plane, in a region where no known stars or structures exist. It was a blank zone, a stretch of space catalogued but largely unstudied because it contained nothing visible. The math suggested that this might be where its journey began. Some researchers dismissed it as coincidence, others called it a clue. A few even proposed that this region might contain the remnants of a long-dispersed cluster, an ancient birthplace of stars that had already scattered. If true, 3/ATLAS could be one of the last surviving fragments from that forgotten structure. Yet as they refined the models further, the curve of its path became almost paradoxical. It didn't behave like a simple gravitational trajectory. Instead, it resembled a folded surface, as though space itself had warped along the way. The deviation wasn't random, it followed a smooth, continuous pattern, like paper bent along a crease. The idea that time and space could fold in this way was not new. General relativity allowed for such distortions. but seeing it implied in real data made the theory tangible. The conclusion was unsettling. The trail backward through time did not lead to a single source. It led to a region that behaved as though the rules themselves had shifted, a place where geometry no longer aligned with expectation. Astronomers didn't claim to have found anything supernatural. They knew space was full of strange gravitational structures, ripples, voids, and warped fields caused by mass and motion. But the implication remained. Somewhere beyond known space there was a region that defied prediction. Something there could bend a trajectory millions of years after it had passed. You imagine them, scientists sitting in dark rooms, eyes fixed on simulations running across endless grids of numbers, watching a line of motion twist around invisible forces. Each new result deepens their curiosity. Each answer adds another question. And as the trail fades into that blank zone, you understand the same thing they do. That the past is not always behind us. Sometimes it curves, leading toward places that cannot be named. When astronomers followed the reconstructed orbit of 3I/ATLAS as far as their equations would allow, they reached a strange conclusion. Its path seemed to lead into a section of the galaxy that had no designation. It was not part of any known stellar association or cluster. Star maps showed almost nothing there. No bright sources, no nebulas, not even faint background stars dense enough to form patterns. The region appeared empty. But empty in astronomy rarely means absence. It often means ignorance. To verify this apparent void, multiple observatories checked the coordinates independently. Optical telescopes saw little more than scattered background noise. Infrared observations revealed only diffuse radiation, a weak uniform glow that didn't vary with position. Radio surveys found faint static without clear structure. It was as if every wavelength agreed on the same point. This part of space contained almost nothing. The location wasn't far from the galactic plane, but it existed in a quiet pocket between the spiral arms, where interstellar density drops sharply. Such voids are common between the filaments of gas and dust that make up the Milky Way's structure. However, this particular void was unusual in size and stability. It extended across several light-years with no sign of star formation or remnant material. Even dark molecular gas, usually detectable through microwave emission, was minimal. Astronomers gave it a temporary designation, an internal code used in databases, but no formal name. It didn't deserve one yet, they said, until something about it could be verified. Still, among research teams, it became casually known as the region without a name. The phrase fit because every attempt to define it failed. To understand what they were seeing, scientists turned to galactic dynamics. The Milky Way is not smooth. It's shaped by gravity, time, and turbulence. Gaps appear where stellar winds clear matter, or where gravity from passing structures pulls material aside. Over billions of years, these motions create cavities in the galactic disk. But those cavities usually have traces, remnants of gas or radiation. This one did not. The absence was too clean, too geometrically consistent. Some theorize that it might be the remnant of a supernova's expansion bubble. When a massive star dies, it can push away nearby material, leaving an empty zone. But analysis showed no surrounding shock fronts, no remnants of heavy elements such as iron or silicon that mark such events. Others suggested a former cluster might have drifted apart, leaving a gap in the star field. But gravitational simulations showed no corresponding increase in stellar motion around it, which would normally occur after such dispersion. The lack of explanation deepened interest. Space agencies allocated observation time on their most sensitive instruments. The European Space Agency used Gaia's star position data to measure the motions of stars near the boundary. NASA's Chandra Observatory searched for faint X-ray sources. None appeared. The region remained statistically silent. To check whether it was truly devoid of matter, scientists turned to gravitational mapping. Even when light fails, gravity reveals presence. By studying the motions of nearby stars and how their paths curved, astronomers could estimate the total mass enclosed in a region. They found something unexpected. The area wasn't just lacking visible matter, it seemed to lack gravitational mass altogether. There was less matter there than predicted by galactic models. In other words, the region wasn't just empty, it was underdense, a true void slightly lighter than the surrounding space. Such voids exist on cosmological scales between galaxies, but within a galactic disk they are rare. Normally, gravity and pressure from surrounding gas would fill them over time. For one to persist meant that something had kept it open, or that it had never contained matter to begin with. This finding sparked an idea. Some physicists proposed that the void might be a local imprint of a larger-scale dark matter fluctuation. Dark matter, though invisible, shapes everything. If a portion of it was slightly less dense in this region, ordinary matter would have fewer gravitational anchors to gather around. Over billions of years, that could create a zone of true emptiness. The Milky Way, though massive, is not uniform. Tiny imperfections from its formation still echo in its structure. While theoretical work continued, observers returned to the practical question. Why did 3I/ATLAS come from here? If the object's path truly passed through this under-dense zone, it meant it had crossed an area with almost no gravitational interaction. That could explain part of its trajectory, the absence of forces to alter its motion. In a region so devoid of mass, an object could travel undisturbed for immense periods, its course remaining nearly straight. To visualize this, scientists created three-dimensional models of local space. They plotted the positions of stars, dust clouds, and magnetic fields. On the display, the void stood out clearly, a smooth gap among the textured filaments of matter. 3I/ATLAS's trajectory, when projected onto this map, cut directly through it. That visual confirmed what equations already implied. The object had travelled through one of the quietest places in the galaxy. In that environment, the usual processes of erosion and collision that alter asteroids would be minimal. No interstellar dust to abrade its surface, no nearby stars to heat or irradiate it. It would retain its original chemistry and structure almost perfectly. In effect, it was a preserved sample from another time. Spectroscopic data supported this interpretation. Compared to typical interstellar material, the object's outer layer showed less weathering. The ratio of volatile compounds remained higher than expected for an object that had spent eons exposed to cosmic radiation. That indicated long-term isolation, precisely what such a void would provide. Still, another question arose. How did such an object enter or leave this void? The edges of the region acted like a boundary between different gravitational environments. If something passed through, its motion might change subtly, enough to be noticed in precise orbital data. Indeed, when astronomers looked again at the small deviations in 3I/ATLAS's path, they found that they coincided roughly with the estimated edges of this void. That alignment was too precise to ignore. The discovery led to a hypothesis that the boundary of the void might not be smooth. Instead, it could contain gradients of gravitational potential, thin zones where the density of matter changes abruptly. These gradients could act like lenses, bending trajectories slightly. Over millions of years, even a minute deflection could alter an object's eventual course by light years. If 3I/ATLAS crossed one such gradient, it could explain the odd curve noticed earlier. To test this, researchers ran simulations of motion through a non-uniform gravitational field. The results matched observations closely. The object's trajectory could indeed have been shaped by such gradients. That meant the void was not completely passive. It interacted, subtly but measurably, with matter that passed through it. This raised philosophical as well as scientific implications. In most of astronomy, regions are defined by what they contain: stars, gas, dust. Here was a region defined by what it lacked. Yet its emptiness had measurable effects. Even absence, it seemed, exerted influence. The research community began to discuss the region more openly. Papers referred to it as a low-density anomaly. Others nicknamed it the Hollow. But no official name was adopted. Naming implies understanding, and there was not enough of that yet. One team proposed sending future missions, distant probes that could, in theory, travel far beyond the heliosphere and approach the region directly. It was only a thought experiment for now, since such distances remain unreachable with current technology. Still, the idea gained attention. If a void could be mapped up close, its boundary could reveal much about the large-scale structure of the galaxy and the distribution of dark matter within it. Meanwhile, 3I/ATLAS continued its journey, now far beyond the reach of most telescopes. Its brightness faded with distance, but its legacy remained. The models built to trace its path were now being applied to study other interstellar visitors, to see whether they too passed through similar underdense zones. If multiple objects shared such origins, it could suggest that these voids were not accidents but integral parts of galactic evolution, places where ejected matter travelled freely between systems. The more scientists examined the void, the more it resembled a transition zone, not merely nothingness, but a bridge between denser regions of the galaxy. In a sense, it connected star systems without belonging to any. It was a kind of galactic neutral ground where gravity whispered instead of shouted, and within that silence the journey of 3/ATLAS gained new meaning. It was no longer just a visitor from elsewhere. It was a product of contrast, a fragment that had drifted through one of the quietest places in the cosmos. The region without a name remained officially blank on maps, but in data and discussion it grew significant. Astronomers understood now that sometimes the most informative places in the universe are those where almost nothing happens. What lies beyond this void, beyond even the thinnest whisper of matter, was the next question they would face. Because when the trail continues past emptiness, the universe begins to show what it hides best. When the data first arrived, no one thought much of it. The light from 3/ATLAS had been split and analysed hundreds of times already, each wavelength sorted, mapped, and catalogued. But the new readings didn't match any known element on the periodic table. At first, scientists assumed it was an error, a calibration issue, maybe contamination on the spectrograph lens. Instruments are sensitive, even a small shift in temperature or dust particle can distort results, so they checked again, and again. Each time the same strange pattern appeared, an emission line that bent slightly off the standard curve, almost as if light itself had changed behaviour. The team at the Mauna Kea Observatory was the first to notice the anomaly. They sent their findings to several other observatories for cross-verification. Within days, data from Chile, Spain, and even the orbiting James Webb Telescope confirmed the same results. Whatever was reflecting sunlight from 3/ATLAS was not composed of any material found in our solar system. Its light signature showed an atomic structure too stable to belong to known heavy elements, yet too reactive to fit into lighter categories. It was as if nature had taken a shortcut between two fundamental rules of chemistry. In science, strangeness often hides within the details. The spectrum's peaks were sharper, cleaner, more symmetrical than anything expected. It suggested an element with a perfectly balanced electron field, something that should collapse under quantum fluctuations but didn't. Physicists began to question whether they were seeing new matter or a new form of organization within existing matter. Some theorized it could be an isotopic variant, an atom with an unusual neutron-proton ratio. But the ratios didn't match any stable isotope model. Weeks passed as labs simulated possible atomic structures using quantum mechanical models. None could reproduce the observed light behavior. A few researchers proposed that the readings could be the result of interaction with an exotic magnetic field, one capable of twisting the polarization of light in ways we don't yet understand. If that was true, then the new element might not be new at all and merely light distorted by the forces beyond our current instrument's ability to measure. Still, there was a deeper unease. Every time they tried to classify it, the data resisted interpretation. It didn't fit within standard atomic tables or known cosmological models. Some called it the resistance pattern. Others began referring to it unofficially as element X. It became the subject of late-night debates, endless recalibrations, and more than a few skeptical editorials. Many believed it was simply an error born from overlapping readings, a statistical fluke that would fade once better data came in. But the data didn't fade. It became stronger as 3/ATLAS moved farther from the sun. Normally, light scattered and weakened with distance. Instead, the anomaly grew clearer, as if isolation from solar radiation made the material more stable. That behavior defied logic. Materials don't become more readable as they move away from energy sources. They become dimmer, harder to track. Yet somehow, this object seemed to thrive in absence, a pattern of resilience that no known compound or mineral had ever shown. NASA scientists began running comparisons with interstellar dust and meteorite fragments collected from Antarctic ice and lunar samples. None matched. The closest resemblance came from certain pre-solar grains, materials older than the sun itself, preserved inside meteorites. Even then, the energy signature of 3I/ATLAS was far more refined, as if forged under conditions too extreme for normal matter to endure. One astrophysicist suggested it might be matter crystallized within a neutron star's outer layers, somehow ejected during a collision event. Another speculated it might have originated in the early universe, when quantum instability allowed the creation of short-lived, exotic atoms that later decayed. If 3I/ATLAS carried remnants of such matter, it would be a window into the universe's earliest chemistry. The implications were enormous. A single verified sample could rewrite atomic theory, fusion models, and possibly even our understanding of dark matter. Yet there was no way to collect such a sample. The object was already far beyond reach, and no spacecraft could catch it. The best humanity could do was observe from a distance, translating light into information and information into meaning. A small group of researchers from CERN began to simulate collisions in particle accelerators that might reproduce the same spectral signature. After thousands of collisions and billions of data points, a partial match appeared, but in the some not exact, but close enough to suggest that 3I/ATLAS might contain quark-level configurations beyond the standard model. If proven, this would mean nature had produced stable matter made from exotic particles thought to exist only in high-energy states. That discovery would redefine what normal matter even means. For a while, scientific journals filled with speculation. Some articles proposed naming it Atlassium, while others argued that doing so was premature. A few fringe theories even suggested the element might not be matter at all, but structured radiation, energy held together in a self-sustaining field. The mainstream community avoided such claims, preferring to focus on testable physics. Still, in private discussions, even the most grounded researchers admitted the truth. They were seeing something that shouldn't exist. In a way, that was the most exciting part. Science advances not through certainty, but through doubt. Every unexpected observation opens the door to a broader universe. The element that shouldn't be might not only change chemistry, it could challenge our idea of what reality allows. By the end of the year, the anomaly was officially documented in multiple observatories' reports and archived for further study. The International Astronomical Union classified it as a sectoral irregularity of non-terrestrial origin. It was a cautious phrase, the kind scientists use when they don't yet understand what they've found. But for those who had seen the data firsthand, it was something more, a hint that the universe still keeps secrets older than its stars, written not in myth or poetry, but in the cold precision of light. When astronomers traced the path of 3I/ATLAS back through time, the simulation suggested something unusual. The trajectory didn't align with any stable orbital region or common ejection model. It didn't come from the Oort cloud or from any known stellar nursery. Instead, its motion hinted at a violent beginning, one involving immense gravitational forces. That led to a hypothesis few had considered seriously. 3I/ATLAS might have been born from the debris of an ancient galactic collision. Billions of years ago, galaxies routinely collided and merged as the universe settled into larger structures. During those interactions, massive amounts of matter were flung into intergalactic space. Some of that debris condensed into stars, some into planets, and some remained as cold fragments wandering indefinitely. Using data from simulations of galactic dynamics, researchers noticed that the probable origin path of 3I/ATLAS intersected with a region near what is now the boundary between the Andromeda and Triangulum galaxies, an area thought to have experienced a close gravitational interaction around 6 billion years ago. That event, according to current models, would have produced vast tidal streams of gas, dust, and rock, stretching hundreds of thousands of light years. Within those streams, shock waves from supernovae and the compression of magnetic fields could have created dense pockets where elements fused and reformed. A fragment ejected at just the right speed and angle could have drifted across the cosmos ever since, never captured by any star system. 3I/ATLAS, it seemed, might be one such fragment, a piece of cosmic shrapnel from a collision so ancient that the galaxies involved no longer resemble what they were. The theory gained traction after astronomers compared its velocity vector to the direction of known tidal remnants in that region. The alignment was not perfect, but close enough to be statistically significant. More importantly, The unique material composition detected earlier, including the mysterious unclassified element, made sense in this context. A galactic collision would expose matter to gravitational forces and radiation levels extreme enough to forge exotic atomic structures. It could explain why the spectral data from 3I/ATLAS showed patterns unseen elsewhere. Scientists began reconstructing possible histories. In one scenario, two spiral galaxies passed close enough that their outer arms intertwined. The interaction triggered bursts of star formation, throwing millions of tons of heavy elements into interstellar space. Within that chaos, some materials could have cooled unevenly, forming compounds never produced in isolated stellar systems. Over time, fragments of those materials might have condensed into rocky bodies. If one of those fragments escaped the gravitational pull of both galaxies, it would have drifted freely through the intergalactic void, effectively immortal. The evidence wasn't absolute, but it fit more than any alternative explanation. 3/ATLAS's high velocity, rare isotopic ratios, and non-standard light reflection all pointed toward an origin in a zone of high energy interaction. Even its current stability, the fact that it survived eons without disintegrating, could be explained by the density and toughness of matter forged in such extreme conditions. Astronomers began calling it a fossil of violence. The phrase captured the paradox, something beautiful and stable created by immense destruction. The concept fascinated not just scientists but philosophers and artists as well. If galaxies could collide and still give birth to new structures, then perhaps chaos itself was a creative force. To test the hypothesis further, computer models simulated how a fragment of that size might have escaped a galactic encounter. The results showed that under the right alignment, a slingshot effect could accelerate debris to intergalactic speeds while preserving its integrity. The simulation also revealed that such fragments could retain traces of the original magnetic fields from the collision, a kind of molecular fingerprint of their birthplace. When researchers examined the polarization data from 3I/ATLAS's light, they detected faint magnetic patterns inconsistent with the interstellar medium it had recently passed through. That suggested it carried an internal magnetic memory, a residual field frozen into its structure since its formation. The field's alignment matched what would be expected from material ejected during a large-scale galactic merger. By this point, the collision theory had become the leading explanation. Papers were published linking it to the broader study of cosmic evolution, proposing that objects like 3I/ATLAS could help scientists understand how material circulates between galaxies. Each piece of intergalactic debris, they argued, might hold a record of early cosmic chemistry, preserved in isolation for billions of years. The data also revealed something subtle: small irregularities in the object's motion, suggesting that its mass was unevenly distributed. That was consistent with being a fragment rather than a fully formed asteroid or comet. Some surfaces appeared unusually reflective, others darker, as if composed of multiple fused materials. Spectroscopic mapping supported this, identifying regions with different atomic structures coexisting in a single body. Such heterogeneity could only occur in an environment of immense compression and rapid cooling, like the aftermath of a massive collision. For many in the scientific community, this discovery changed the way they viewed space debris. Instead of random rocks drifting between stars, some might be historical artifacts, geological records of events that shaped galaxies. A single object like 3I/ATLAS could tell a story that stretched across cosmic time, linking the distant past to the present. By the time the findings were consolidated into official reports, the public had taken a strong interest. Documentaries began describing it as the shard of a broken galaxy. The phrase captured both the magnitude of the event and the emotional resonance it carried. Humans, after all, are drawn to stories of survival, and 3I/ATLAS was a survivor on a cosmic scale. Even after the data was reviewed and refined, one question remained open. What caused the initial ejection? Was it a supernova blast, a gravitational tug from a passing cluster, or something else entirely? The answer was still beyond reach, but for now, scientists were content with knowing that they had found a messenger from a time when galaxies collided, stars were born, and the universe learned to recycle its own chaos. The study of 3S/ATLAS took a new turn when researchers began questioning the forces guiding its motion. Traditional gravitational models could not fully explain the way it accelerated and decelerated as it passed through interstellar space. Its velocity shifts were minute but measurable, and they persisted even after accounting for the gravitational effects of nearby stars, dark matter estimates, and solar influence. The question became simple yet profound. What exactly was pulling it, or was it even being pulled at all? At first, many suspected observational error. Instruments were recalibrated, data was cross-checked, and simulations were rerun using multiple gravitational models. The irregularities remained. The more precisely astronomers measured the path of 3S/ATLAS, the clearer it became that something subtle was acting on it. It wasn't enough to alter its general course, but it was enough to challenge Newtonian expectations. This led to the revival of an old debate in astrophysics, whether gravity could be more than a simple geometric curvature of space-time or a measurable pull between masses. Some researchers proposed that what appeared as gravitational attraction might, in some cases, be a byproduct of deeper physical relationships, perhaps linked to quantum fluctuations or to the fabric of space-time itself, storing information about matter long after that matter had moved elsewhere. The working term for this was gravitational memory. The idea suggested that when two massive bodies interacted, space-time retained a residual pattern, a kind of echo of that event. Over time, this echo could exert a faint influence on objects passing through, not as a physical force, but as a bias in how space-time curved. In essence, the universe might remember where things once were. If this was true, then 3S/ATLAS could be responding not to visible gravity, but to these invisible patterns, traces of ancient structures or collisions long gone. That might explain why its motion didn't align perfectly with current gravitational maps. It was, in a sense, following paths written billions of years ago, moving through space shaped by forgotten events. Astrophysicists at multiple observatories began collaborating to analyze this possibility. They mapped regions along 3I/ATLAS's trajectory using data from gravitational lensing surveys. Those maps revealed faint distortions in space-time consistent with concentrations of dark matter, or with the residual ripples left by galaxy-scale interactions. To the surprise of many, several of these distortions aligned precisely with the object's path. This suggested that the object might be moving along a corridor of ancient gravitational influence, the ghost trail of a galactic merger. These residual distortions wouldn't pull in the traditional sense, but could guide trajectories subtly, like grooves carved into a record. The metaphor was compelling. 3I/ATLAS wasn't being pulled forward. It was gliding along the memory of forces that no longer existed. This concept reframed the object's entire journey. Rather than a random fragment drifting through chaos, it might be a traveller moving through the universe's historical landscape, a landscape shaped not only by matter, but by the memory of matter. Gravity, in this context, was not just a force but an imprint. The theory attracted both interest and criticism. Skeptics argued that the observed variations were too small to justify such a radical interpretation. They pointed out that solar radiation pressure, cosmic dust collisions, or unmodelled outgassing could also explain the anomalies. However, these explanations didn't fully fit the data. 3I/ATLAS lacked the volatile compounds needed for significant outgassing, and its reflective surface reduced the effect of solar pressure. As more data accumulated, the gravitational memory hypothesis gained cautious support. Researchers began simulating how regions of space might retain such residual curvatures after large-scale mass movements. The simulations showed that after a major galactic event, such as a merger or a collapse, space-time distortions could persist for billions of years. They would be extremely weak, but detectable with precise enough instruments. One particularly interesting finding was that these distortions could overlap, forming interference patterns in space-time curvature. When a small object like 3I/ATLAS moved through them, its path could deviate slightly, as if nudged by unseen hands. This could create exactly the kind of irregular velocity changes astronomers were observing. To test this further, a new research initiative began using pulsar timing arrays, systems that detect minute gravitational variations by observing the consistent signals from pulsars. If 3I/ATLAS really was influenced by residual curvatures, the same distortions might be measurable in pulsar data. Preliminary results hinted at correlations, though they were not yet definitive. The implications of this theory extended far beyond a single object. If space-time truly stored such memory, then the universe itself functioned as a kind of archive, every event leaving an imprint on the structure of reality. Regions of apparent emptiness might still carry the history of forces that once shaped them. It also meant that every object, including Earth, might be subtly guided by the lingering gravity of ancient stars and galaxies. In this context, absence became a physical phenomenon. The void between galaxies wasn't truly empty, it was filled with the memory of what had passed through. 3I/ATLAS, then, wasn't just responding to current forces but navigating through this invisible record. Its trajectory was both a motion through space and through history. The more scientists discussed this, the more philosophical the conversation became. If gravity could act as memory, then perhaps the universe never truly forgot anything. Every mass that moved, every collapse or collision, left a faint trace, not lost but diffused through space-time. Some began referring to this concept informally as the gravity of absence, a phrase describing how even what no longer exists can still exert influence. By the time the research reached peer review, multiple observatories had confirmed the same small but consistent anomalies. The case for gravitational memory remained unproven, but increasingly plausible. 3I/ATLAS had become a natural experiment, a rare opportunity to test theories about how the universe preserves its own past. For many astronomers, the discovery reshaped how they thought about cosmic structure. The universe was no longer a static arena where matter moved freely. It was a dynamic continuum shaped by every motion that had ever occurred. In that sense, the cosmos was self-referential, constantly influenced by the memory of its own history. As 3I/ATLAS moved farther away from observable range, the data grew sparse, but its influence on scientific thought deepened. Research groups began proposing missions to detect other interstellar objects that might display similar anomalies. If more were found, the gravitational memory model could move from speculation to accepted theory. By the end of the decade, papers on the topic were among the most discussed in astrophysics conferences. The object itself was gone, vanishing into the darkness between stars, but its passage had left behind more than just data. It had changed the way humanity understood gravity. In the simplest terms, 3I/ATLAS revealed that the universe might remember. Even in the emptiest spaces, there are traces of everything that once was. Gravity, it turned out, was not only a force of attraction, but also a whisper from the past, a record of existence guiding what still remains. When astronomers lost direct sight of 3I/ATLAS, its projected path placed it in a region between galaxies, an area so vast and thin that even light from the nearest stars took centuries to cross. These intergalactic spaces are often misunderstood as empty, but they are not. They contain a faint mix of hydrogen, helium, trace elements, and dark matter. The density is astonishingly low, yet these sparse atoms stretch across billions of kilometers. In this environment, 3I/ATLAS continued its journey without noticeable interference, moving through what could be described as the quietest part of the universe. To understand why these regions are so still, scientists often compare them to the voids in cosmic web structures. The large-scale structure of the universe resembles a three-dimensional web made of galaxies and dark matter filaments. Between these filaments are vast gaps known as voids. Inside them, gravitational pull is minimal because matter is scarce. 3I/ATLAS was now likely travelling through one such void, an area where no known stars, planets, or major gravitational sources existed nearby. The temperature in such space is only a few degrees above absolute zero. It is dominated by the cosmic microwave background, the faint radiation left over from the Big Bang. The object's surface, once warmed slightly by solar light during its passage near the Sun, would have cooled rapidly. Its atoms would contract fractionally, stabilizing into the deep cold equilibrium that defines intergalactic travel. Despite the stillness, these voids are not lifeless. high-energy particles known as cosmic rays pass through constantly, originating from distant supernovae and active galactic nuclei. They move close to the speed of light, occasionally colliding with dust particles or atomic fragments. For 3I/ATLAS, each of these collisions was like a grain of sand brushing against a mountain, negligible in effect but constant in presence. Over millions of years, such impacts could alter its surface, smoothing microscopic ridges and changing its chemical composition slightly. As it moved deeper into intergalactic space, gravitational influence from the Milky Way decreased, replaced by the weaker but cumulative pull of the local group of galaxies. Its path, though nearly straight, curved subtly in response to these distributed forces. If one could trace that curve with precision, it would describe a long arc bending toward the center of the mass of the local group, a region dominated by the Andromeda and Milky Way galaxies. Yet given its speed, 3/ATLAS would not be captured. It would simply continue past, crossing the thin gravitational boundaries that separate one galactic system from another. From an observational standpoint, this stage of its journey was almost impossible to follow. The object had become too faint for optical telescopes, and its infrared signature was lost against the background radiation. Only its predicted trajectory derived from previous data allowed scientists to estimate its position. Occasionally, radio observatories searched for any reflected or emitted signals, but none were detected. The silence was complete. This silence is not an absence of activity, but rather a state of extreme balance. In the intergalactic medium, particles are so far apart that they rarely interact. Photons can travel for billions of years without striking anything. Even magnetic fields, which are common within galaxies, become diffuse here, stretched across unimaginable distances. The result is a kind of perfect equilibrium, a place where change occurs, but at an almost immeasurable rate. From a physical perspective, this environment offered a unique opportunity to study the boundary conditions of the universe. Researchers theorize that objects like 3I/ATLAS could help test the limits of particle decay, atomic stability, and the persistence of materials under constant exposure to cosmic radiation. By modeling its journey, they could estimate how long certain molecular structures might survive in deep space. The findings could inform not only astrophysics but also material science and the study of long-term spacecraft durability. In a sense, 3I/ATLAS had become a probe not by design, but by existence. Every interstellar object carries within it a record of the environments it has passed through, the isotopic ratios of its elements, the layering of micro-impacts, and the erosion patterns on its surface all preserve information. If another civilization ever found it, they could reconstruct its history much like archaeologists study fossils or meteorites. Some scientists began to think of such objects as natural messengers. They move from one galactic system to another, crossing boundaries that light and gravity can only influence but not transport matter across easily. In their structure lies the memory of multiple cosmic environments. 3I/ATLAS, like others before and after it, connects regions of the universe that would otherwise remain isolated. The intergalactic void also presents challenges to theoretical models. For example, the distribution of dark matter within these regions remains uncertain. Some models predict that even in the emptiest spaces, filaments of dark matter persist, creating weak gravitational gradients. These gradients might subtly influence the trajectory of any object passing through. Though undetectable directly, their presence could be inferred from long-term motion studies. If 3I/ATLAS experienced any acceleration changes inconsistent with known mass distributions, it could provide indirect evidence of such filaments. Over time, the significance of this phase in its journey became more philosophical than observational. The void, while physically empty, represented a boundary of knowledge. It illustrated both the vastness of what science could measure and the enormity of what remained unknown. Every model, every map stops somewhere, not because the universe ends, but because measurement reaches its limit. Beyond that, only inference and imagination remain. The quiet between galaxies is not a pause, but a continuation in a slower rhythm. Matter still moves, energy still flows, but in a way that emphasizes duration over change. It is a reminder that the universe operates on scales that exceed any human sense of time. What seems like stillness is simply motion stretched thin across billions of years. For 3I/A TLAS, this was the longest and most uneventful stage of its existence. It would travel through the void for perhaps millions of years, untouched, unseen, unmeasured. Its composition would remain stable, its direction mostly unchanged. It would eventually enter another region of space, perhaps influenced by another galaxy's pull, or it might continue indefinitely, carrying within it traces of the systems it had once passed. Even though no instruments could follow it now, its journey continued, demonstrating the persistence of motion and matter in a universe where even silence has structure. Somewhere between the faint pull of galaxies and the steady background of radiation, 3I/ATLAS moved on. Another reminder that the spaces between things often hold the deepest truths. Astronomers began the process of mapping the region through which 3I/ATLAS was predicted to pass. The task seemed straightforward at first. Gather all known data from nearby galaxies, gravitational influences, and background radiation, then model the trajectory. But as the calculations deepened, the limits of their models became clear. Each new layer of precision revealed another form of uncertainty. The problem was not with the data itself, but with how space behaves on scales this large. At intergalactic distances, even light bends slightly under the influence of invisible masses, the dark matter that threads through the universe. When researchers tried to trace a straight line, they found that their instruments were following curves. Coordinates shifted subtly, as if the universe itself refused to be pinned down by human geometry. They described the phenomenon as lensing distortion, but even that term simplified the truth. The light from distant galaxies passed through layers of invisible structure, refracting and scattering like sunlight through glass. Every model corrected one error only to introduce another. Positions drifted, distances blurred. What looked solid in one wavelength appeared stretched in another. The very act of observing seemed to alter what was being observed. Astrophysicists compared notes from observatories across the globe. Infrared readings from Chile didn't align with optical readings from Hawaii. Space-based instruments confirmed some details and contradicted others. 3I/ATLAS, far beyond measurable range, became the reference point for an entire debate about how the cosmos could be mapped when even its background refused stability. This wasn't a failure of technology, it was a demonstration of how nature resists simplification. Every coordinate system assumes a fixed framework, a baseline against which all movement can be measured. But at this scale, no fixed framework exists. Space itself expands, time itself stretches. Even if astronomers froze the universe at a single instant, the reference grid they'd draw would already be outdated by the time the calculation finished. When the team from the European Southern Observatory published their preliminary findings, they used an unusual term in their report: topological fluidity. They described regions of space-time that behaved like dynamic surfaces rather than static maps. Distances could not be defined precisely because space and gravity interacted continuously. What appeared as an empty void on one scale could, at higher resolution, reveal thin threads of matter, invisible highways of dark energy and cold gas. For the first time, mapping the path of a single interstellar object required confronting the flexibility of reality itself. No one could say exactly where 3/ATLAS was, only where it was likely to be within a range defined by probability, not certainty. It was a sobering realization. Even the most precise instruments could only sketch outlines around the unknown. As data accumulated, computational models grew in complexity. Supercomputers ran simulations that incorporated billions of variables, from galactic mass distributions to the quantum noise of background radiation. Yet the results still produced ambiguity. Some simulations predicted that the object would curve slightly toward a dark matter filament. Others suggested it would pass through an unbound region entirely. In both cases, the difference amounted to millions of light years over time, a measure both vast and negligible depending on perspective. This ambiguity forced scientists to reconsider what it meant to chart the universe. For centuries, astronomy relied on the assumption that the cosmos could be mapped like a territory, with edges, distances, and coordinates that could be known with increasing precision. Now, that assumption cracked. The universe was not a territory but a process, and mapping a process required a different language. Mathematicians stepped in, introducing new geometric frameworks based on non-Euclidean principles. They proposed models where coordinates existed not as points but as relationships, where distance was defined by interaction, not by space alone. In these models, 3I/A, TLAS's path could be described as a series of dynamic transformations through an evolving space-time field. The numbers worked, but they raised a philosophical question. If a map constantly changes with its subject, is it still a map or simply a record of movement? This question reached beyond mathematics. Linguists and philosophers joined the discussion, suggesting that human language itself might be unfit to describe infinite structures. Words like edge, center, and direction assumed boundaries that didn't exist. The moment one tried to express infinity, the concept broke into paradoxes. Every description of nothingness implied the existence of something to contrast it with. One research paper, circulated informally among scientists, summarized the challenge in plain terms. We can measure the curvature of the universe, but we cannot describe its totality. To do so would require a viewpoint outside the universe, something no observer can have. That limitation, though frustrating, also inspired awe. The attempt to map infinity forced humanity to recognize its own scale. Students studying the data began to notice that despite the mathematical noise, certain patterns repeated. The distortions of light through the cosmic web followed recognizable ratios, echoes of structure seen at smaller scales, such as in the clustering of galaxies and the shapes of molecular clouds. It was as if the universe repeated its architecture in every dimension, from the smallest to the largest. These observations didn't solve the mapping problem, but they suggested that order persisted even within apparent chaos. Some scientists speculated that if one could model these repeating structures precisely enough, they could predict regions of stability, gravitational eddies, where interstellar objects might slow or change course. If 3I/TLAS ever passed through such a region, its motion might record subtle gravitational patterns that no telescope could observe directly. It would be an unconscious witness to the shape of the cosmos itself. To the public, this idea captured imagination more than the technical data ever could. The image of a lone object sailing through an uncharted void while carrying traces of cosmic structure became a powerful metaphor. Museums and educational programs began to describe 3I/ATLAS as a map without borders, a moving reference for what could never be fully mapped. Still, within scientific circles, the frustration persisted. Observatories wanted precision, not poetry. Funding agencies wanted numbers, not metaphors. Yet with every new dataset, the line between physics and philosophy blurred further. Even the most rigorous physicists admitted that describing the universe's totality required more than equations. It required imagination. At one international conference, a senior cosmologist summarized the issue in a sentence that became famous among his peers. "Our coordinates blur because our perspective does." He meant that every measurement depends on where and how it's made. Since humans exist inside the universe, not outside it, every map they draw includes themselves. The distortion is not just physical but existential. In the end, the mapping of 3I/ATLAS's route became less about locating an object and more about confronting the nature of knowledge. Scientists realized that uncertainty was not an obstacle but a fundamental feature of reality. The universe could be known only in fragments, through shifting reference frames and partial truths. Absolute precision belonged to theories, not to the world itself. The final report, after years of study, did not conclude with exact coordinates. Instead, it included a statement rarely found in scientific literature. There are regions where description itself becomes an approximation of wonder. It was both a confession and a celebration, an acknowledgement that some aspects of existence can be traced only by curiosity, not by mathematics. In that sense, the effort to map the void achieved its purpose. It reminded humanity that every discovery reveals both what is known and what remains beyond comprehension. The map without borders was not a failure of science but its truest expression, the ongoing attempt to understand a universe that refuses to stand still long enough to be defined. When astronomers talk about the universe, they often describe it as expanding, a term that suggests something constant, steady, and predictable. But in reality, the expansion is not uniform. It accelerates and slows in subtle ways depending on the distribution of matter, energy, and dark forces that remain poorly understood. To describe this behavior, physicists began referring to it as a cosmic pulse, a rhythmic cycle of motion that shapes the universe on every scale. For centuries, humans assumed the universe was static, a fixed system of stars and galaxies bound together in timeless balance. That belief changed with the discovery of redshift. When light from distant galaxies was observed to stretch toward the red end of the spectrum, it became clear that those galaxies were moving away from us. The universe was not fixed, it was breathing outward. Later, with the study of the cosmic microwave background radiation, scientists confirmed that this motion had begun nearly 13.8 billion years ago with the Big Bang. However, more recent data from deep space observations, especially those from the James Webb Space Telescope, have shown irregularities. The rate of expansion, measured through what is called the Hubble constant, seems inconsistent depending on the method used. One calculation based on nearby galaxies gives a different number than one based on the early universe. This disagreement, often called the Hubble tension, has become one of modern cosmology's biggest challenges. It suggests that something within the cosmic structure is influencing expansion in ways not yet accounted for. Some researchers hypothesize that the cause lies in dark energy, the mysterious force that makes up roughly 68% the universe's total energy density. Dark energy is thought to drive the acceleration of the expansion, but its exact nature remains unknown. It could be a cosmological constant, a property of space itself, or it might vary over time, acting more like a dynamic field. If it fluctuates, those fluctuations could create what we perceive as pulses, gradual increases and decreases in the rate of universal expansion. Data collected from supernovae, quasars, and gravitational lensing supports this idea in part. Observed at different epochs, the universe appears to go through phases where its expansion rate changes slightly. On the scale of billions of years, these changes resemble a slow heartbeat, not in the biological sense, but as a pattern of cosmic rhythm. The term pulse became a convenient metaphor for describing these alternating phases of acceleration and balance. The concept gained traction when computer simulations modeled the evolution of the universe using variable dark energy densities. The results showed periodic oscillations in large-scale structure formation. Galaxies formed, merged, and dispersed according to a sequence that repeated on extremely long timescales. These patterns indicated that the universe might not expand endlessly in a smooth line, but could experience cycles of acceleration influenced by hidden physical parameters. When scientists studying 3I/ATLAS compared its movement to the background expansion of space, they noticed something peculiar. The object's acceleration relative to gravitational reference points did not align perfectly with expectations. Tiny deviations, almost immeasurable, suggested that it might be moving within a region where space itself expanded slightly faster than in neighboring regions. The variation was so minute that most instruments couldn't confirm it directly, yet the anomaly persisted across multiple data sources. This observation led to a controversial hypothesis. What if local fluctuations in the cosmic pulse could influence smaller structures, even individual objects? If so, 3I/ATLAS might be carrying evidence of these fluctuations, its trajectory subtly affected by the universe's own rhythmic behavior. Physicists began running simulations that introduced microscale variations in spacetime expansion. They wanted to test whether these variations could explain the observed path of the object. The early results were inconclusive but promising. Even a small change in the background expansion rate could shift an object's motion over interstellar distances by measurable amounts. If confirmed, this would mean that no object truly moves through a neutral space. Every region of the universe vibrates with slightly different tension, as though space itself were alive with motion. The connection between expansion and matter became a focus of study. Energy density and gravity interact constantly, one trying to pull everything together, the other pushing it apart. The dynamic balance between them determines the structure of the cosmos. When dark energy slightly overpowers gravity, the universe accelerates. When gravity dominates locally, structures like galaxies and clusters form. It is this continuous struggle that creates the universe's pulse. To model the phenomenon, researchers used analogies from fluid dynamics. They imagined space-time as a flexible fabric with waves of tension moving through it. Each wave corresponded to a shift in the balance of forces. These waves were not oscillations in time like sound, but variations in the geometry of the universe itself. In some regions, the geometry stretched faster. In others, it lagged. The combined effect produced large-scale fluctuations that echoed across billions of light-years. For most people, these ideas were abstract, but when visualized using data simulations, they became more intuitive. Color-coded maps of the observable universe displayed regions of slightly higher or lower expansion rates, forming vast, interconnected zones of motion. The picture resembled a living system, not in a mystical sense, but as a complex network of feedback loops. In this framework, galaxies were not static islands, but moving parts of a much larger mechanism. 3I/ATLAS became an example of how even small bodies might participate in that mechanism. Its velocity, direction, and interaction with surrounding dust could reveal information about local spacetime conditions. By analyzing the changes in its spectral signature, researchers hoped to detect evidence of these cosmic pulses directly. The effort required precise calibration of instruments and long-term observation. Some teams proposed launching a deep space probe to follow a similar trajectory and measure the faint gravitational gradients that define such regions. Meanwhile, theorists explored the implications of a universe that behaves rhythmically. If expansion is not constant, then its ultimate fate might differ from current predictions. In one scenario, if dark energy weakens over time, the expansion could slow, leading eventually to gravitational recontraction, a big crunch. In another, if the energy strengthens, it could drive matter apart completely, resulting in the Big Rip. A third possibility is oscillation, cycles of expansion and contraction extending indefinitely, each one a cosmic heartbeat lasting trillions of years. In this view, the universe is not heading toward a single end, but continually renewing itself through vast natural processes. Each pulse would give rise to new structures, destroy old ones, and set the stage for the next. Though these ideas remain speculative, they align with observed periodicities in large-scale matter distribution. The more scientists examine these possibilities, the more they recognize that describing the universe as static or linear might be misleading. A rhythmic, self-regulating universe explained many anomalies, including the Hubble tension and the formation rate of galaxies. It also provided a framework for interpreting objects like 3I/ATLAS as messengers from dynamic regions of spacetime, carrying evidence of subtle energy flows that mathematics alone struggles to capture. To the researchers working on these problems, the phrase pulse of the universe no longer sounded metaphorical. It became a practical way to explain how the fabric of reality evolves through cycles of balance and imbalance, expansion and containment. What once seemed poetic was now a measurable property of cosmic dynamics. By the end of their analysis, the team studying 3I/ATLAS concluded that its motion could be modeled accurately only if the background spacetime itself was treated as variable. They published their results with cautious wording, acknowledging uncertainty but emphasizing potential. Their findings hinted that the object's path might reflect the broader behavior of the universe, a pattern that connects the smallest trajectories to the grandest scales. For the scientific community, this marked a shift in perspective. The cosmos was no longer viewed as a single event expanding outward from an origin, but as an ongoing process shaped by repeating fluctuations. The pulse was not a metaphor for life. It was a recognition that the universe itself operates through continuous change. Every galaxy, star, and particle participates in that process, not as isolated entities but as expressions of the same evolving field. And somewhere in that field, 3I/ATLAS continued on its path, a solitary witness to the rhythm of everything. Wonder has always been the beginning of science. Every discovery starts with a question that seems too large for an answer. Scientists do not begin with certainty, they begin with curiosity. It is a quiet impulse, not loud or dramatic, but steady. You can imagine the astronomers studying 3I/ATLAS, sitting before their monitors, lines of data unfolding across their screens. They know they are looking at something rare, maybe something that will challenge what they have learned. Their task is to turn that sense of amazement into structured thought. When scientists first observed 3I/A TLAS, they did not start by assuming what it was. They began with what they could measure: light, velocity, trajectory, and composition. These were facts, not guesses, but the moment they saw that its movement and reflection did not fit with known models, their sense of wonder deepened. It was not a failure of knowledge, it was an opening. Science progresses because it allows room for the unknown. The feeling that something doesn't fit is not discouragement, it is motivation. Throughout history, the same emotion has guided discovery. Isaac Newton watched an apple fall and wondered about gravity. Galileo pointed his telescope at the night sky and realized that the planets were not perfect spheres. Marie Curie held a piece of glowing radium and wondered what made it shine. None of them could see the entire picture at first, but they followed the same method: to ask, to test, to observe, to revise. Wonder becomes the foundation of every scientific process because it keeps the human mind from closing too early. The researchers studying 3I/A TLAS know that their measurements may never be complete. They are looking at an object that is already leaving the solar system, but each observation adds one more piece to the larger story of how the universe works. When the telescope captures its faint light, they convert that light into spectra, long graphs of wavelengths showing chemical fingerprints. Normally, this pattern reveals elements like carbon, oxygen, or silicon, but in 3I/A TLAS, the lines do not align perfectly with any known substance. That mismatch is not a mistake. It is the trace of something new, and it reignites the same old emotion that has driven human inquiry since the beginning: the urge to understand. Wonder is not the opposite of logic. In fact, it is what makes logic possible. Without the emotional drive to ask why, no one would spend years studying equations, calibrating instruments, or analyzing noise in the data. In laboratories and observatories around the world, scientists live in a balance between awe and discipline. They feel amazed by what they see, but they translate that feeling into repeatable experiments. In this way, science turns imagination into structure. A sense of wonder is not a distraction, it is a compass. The case of 3I/A TLAS shows how this balance works in real time. When astronomers published their first findings, they avoided using emotional language. Their report spoke of luminosity, albedo, and spectral deviation. Yet between the lines, there was excitement. The raw data hinted that something fundamental might be missing from existing models of interstellar matter. Some researchers compared its readings to those of other visitors, such as Oumuamua or Borisov, but the differences remained unexplained. Each failed comparison did not end the search, it refined it. Wonder is most productive when it coexists with patience. The scientific community thrives on collaboration. A single observatory can detect an object, but many others must confirm it. As data from Chile, Hawaii, and South Africa began to merge, new interpretations formed. Some thought the unusual spectrum could come from extreme cosmic radiation, altering its surface. Others believed it could contain material from a region of space we have never observed directly. These ideas did not contradict one another. They represented the expanding boundary of what could be considered possible. Every explanation begins as a hypothesis, and every hypothesis begins as a question born from wonder. You may think of science as a field of answers, but in reality, it is built from questions. Each time one answer is found, it creates two more questions. When you study something like 3I/A TLAS, you are not just learning about one comet-like object, you are learning how to ask better questions about the universe itself. What conditions could create such a body? How far from known stars must it have formed? How many others might pass unnoticed between galaxies? These are not abstract thoughts. They shape how we design instruments, where we point telescopes, and how we plan future missions. Wonder directly drives technology. There is also a psychological side to this process. Scientists often experience moments of doubt. The universe is vast and progress can feel slow. But those who stay in the field do so because they never lose that small internal spark, the belief that every new observation is part of something meaningful. In this sense, science becomes a form of hope. Wonder is not just intellectual curiosity, It is emotional endurance. It allows the human mind to look at something incomprehensible and say, I can try to understand. In modern science, this emotion is carefully managed. Researchers learn to express it through precise writing and cautious conclusions. But beneath the surface of every published paper is the same quiet amazement that once led early humans to look up at the stars. This continuity connects all eras of discovery. From Stone Age observers to astronomers controlling robotic telescopes across oceans, the feeling is identical. The difference lies only in the tools. 3I/ATLAS as an object may eventually disappear from view. Its data will remain, graphs, models, and archived images. Future scientists will read those records and try to find patterns we cannot yet see. They will use instruments more advanced than ours, and perhaps one day, they will find the same strange spectral lines in another object. When that happens, they will recognize the signature and trace it back to these early observations. This continuity is the true legacy of wonder, knowledge passed from one generation to the next, each building on the curiosity of those before. The science of wonder does not aim to end mystery. It aims to deepen understanding. The more we learn, the more we realize there is still to know. This awareness is not frustrating. It is liberating. It reminds us that human knowledge is a growing structure, not a completed one. The story of 3I/ATLAS is only one example, but it represents a truth that applies to all discovery, that every mystery solved expands the horizon of what remains unsolved. As the telescopes turn toward other parts of the sky, astronomers keep 3I/ATLAS in their memory. They move forward not because the mystery is gone, but because it continues to evolve. In that movement lies the essence of science, to keep asking, to keep refining, and to let wonder remain the quiet engine of understanding. You focus on a single atom from 3I/ATLAS. It may be iron, carbon, or oxygen. Its exact composition still uncertain, but that does not matter for the moment. What matters is what it represents. A fragment of matter that has crossed light years, possibly eons, to reach human attention. Scientists study its charge, its mass, its isotopic ratio. Each value contributes to a database, one number among many. Yet even as those values accumulate, you realize that science alone cannot describe what it means for this particle to exist here, now, within human perception. The research teams treat it as a data point. They use spectrometers to measure its emission lines and identify how it interacts with sunlight. The readings reveal that this atom has undergone exposure to radiation beyond typical interstellar levels, suggesting it may have originated near a high-energy region, perhaps close to a supernova remnant or an energetic stellar wind. These details help astrophysicists model the possible birthplace of 3I/ATLAS. Still, no equation can fully capture the quiet strangeness of matter that has travelled across the galaxy and landed in our instruments. You imagine that this atom, so small that no microscope could isolate it individually, has carried within it the history of countless cosmic events. Inside its nucleus are protons and neutrons forged during earlier generations of stars. Each collision, fusion, and decay was part of a sequence that began long before Earth formed. The particle is, in a literal sense, ancient. When you think about its age, you understand that human history is a momentary flash by comparison. Civilizations rise and fall while this particle continues to drift in cosmic stillness. The scientists at observatories around the world begin comparing models. Some propose that the composition hints at an interstellar molecular cloud origin, while others believe it could come from a more distant intergalactic source. In either case, 3I/ATLAS represents something unfamiliar, an object that has not followed the gravitational patterns expected of ordinary comets. Its path suggests that it entered the solar system from beyond our galaxy's plane, perhaps even from another stellar association altogether. For researchers, this raises critical questions about how small bodies move through interstellar space and what physical forces influence their trajectories. For writers and thinkers outside of science, however, 3I/ATLAS means something different. It becomes a metaphor, a story about movement and isolation, about discovery and meaning. You notice that the same atom that physicists describe with numbers also inspires poets to describe wonder. One sees a charge of +1, Another sees the persistence of existence. These are not conflicting interpretations, they are complementary. Each language, the scientific and the poetic, attempts to describe truth from a different angle. Science quantifies reality, while poetry translates experience. In university classrooms, discussions emerge that blend astrophysics with philosophy. Students talk about how an atom that originated before Earth might remind humanity of its shared material origin with the universe. Every cell, every drop of water, every breath contains atoms that were once part of stars. The line between scientific fact and personal reflection blurs, not because of confusion, but because understanding the cosmos inevitably involves emotion. You cannot separate curiosity from awe. During one conference, a physicist states that the ultimate goal of research is accuracy. A poet in the audience replies that the ultimate goal of writing is meaning. Their conversation is not an argument, but an exchange. The scientist explains how measurement reveals the laws that govern particles, while the poet explains how those same particles shape human perception of beauty and time. You begin to see how both are correct. Knowledge without meaning is incomplete. Meaning without knowledge lacks foundation. In laboratories, analysis continues. Detectors confirm that particles from 3I/ATLAS contain isotope ratios inconsistent with typical solar system materials. This reinforces the theory that the comet originated in another star system. To some researchers, this discovery opens the door to understanding how material from other planetary systems travels between stars. To others, it is a reminder that the boundaries humans assign to systems, solar, galactic, or otherwise, are conceptual conveniences. Nature does not obey human categories. As the data accumulate, the research papers begin to appear in journals. Titles describe spectral signatures, density estimates, and dynamical models. The tone of each paper is precise, measured, objective. Yet behind that objectivity lies genuine excitement. Scientists rarely express emotion in formal writing, but everyone involved knows how extraordinary this finding is. The atom from 3I/ATLAS is evidence that matter is not bound by borders. It drifts freely, indifferent to human definitions of home or origin. Outside the world of academia, public interest remains high. Documentaries describe the journey of interstellar material. Teachers use 3I/ATLAS as an example of how observation and curiosity lead to discovery. Students create art projects imagining what it might look like close up. Even though the object itself is millions of kilometers away, its story becomes a shared cultural event. It connects people who might otherwise never have thought about space at all. You realize that both the scientific data and the creative interpretation serve the same human need: to understand. Whether through numbers or narratives, the goal is comprehension, to make sense of existence and find our place within it. When you hold both perspectives at once, the picture becomes richer. The universe is not just a system of particles, it is also a system of meanings. In reflecting on this, you begin to see that discovery is not only about what lies beyond Earth, but also about what lies within human thought. Every observation changes not just the database, but also the observer. The more deeply scientists look into the physical world, the more questions arise about purpose and perception. That is why the boundary between the particle and the poet is artificial. Both look at the same universe using different instruments, one a telescope, the other language. Eventually, the measurements of 3I/ATLAS reach a point of completion. The instruments have gathered all the data they can. The comet continues its journey outward, moving beyond detection range. But the work it inspired continues on Earth. Researchers continue refining their models. Writers continue reinterpreting its meaning. The atom from 3I/ATLAS remains somewhere out there, perhaps drifting through the void, perhaps merging with another dust cloud. Yet in a real sense, part of it remains here, in equations, in essays, in thoughts. You conclude that the difference between science and poetry is not about fact versus fiction. It is about the methods used to reach understanding. Science begins with observation and moves toward explanation. Poetry begins with perception and moves toward expression. Both, in their own ways, reveal the structure of truth. When you consider that, something within you opens, not as a feeling of mysticism, but as a recognition that knowledge and wonder are not opposites. They are partners in the same human endeavour to make sense of the universe. After months of study, the data from 3I/ATLAS stops changing. Its trajectory has been mapped, its composition measured, and its passage through the solar system documented in detail. For most scientific projects, this would mark the end of observation. But something about 3I/ATLAS continues to disturb expectations. Its path through space does not match any known model of interstellar object motion. It accelerates in subtle ways, not enough to suggest artificial propulsion, but enough to make physicists question whether all forces at play are fully understood. This uncertainty becomes the basis for a larger question, one that extends beyond astrophysics. If 3I/ATLAS came from a region that current models cannot easily explain, then what else might exist beyond the range of our observation? It is a simple question, but it reshapes the boundaries of modern science. Every time humanity encounters an anomaly, a new branch of understanding begins. In this sense, 3I/ATLAS is not just a comet, it is a challenge to existing frameworks of knowledge. At research institutions around the world, the analysis continues. Astronomers debate whether the object's origin lies within the Milky Way or from intergalactic space. If it did come from another galaxy, that would imply that small bodies can travel across immense cosmic distances without being destroyed. Such an event would change how scientists think about the exchange of matter between galaxies. It would also mean that 3I/ATLAS carried material formed under entirely different conditions, perhaps even containing isotopic patterns unknown in our region of the cosmos. The question spreads beyond the laboratories. It becomes a subject of discussion in universities, media reports, and online forums. The public is fascinated by the idea that something from beyond the galaxy might have visited the solar system. For many, the scientific details are secondary to the broader implication that the universe may be filled with travellers like 3I/ATLAS, moving silently through space and occasionally crossing paths with worlds like ours. This thought alters how people imagine the cosmos, not as a static expanse, but as a dynamic system full of motion and exchange. For scientists, curiosity drives them deeper. They begin re-examining data from previous comet observations, searching for patterns that may have gone unnoticed. The more they look, the more they find slight irregularities, small anomalies that could point to interstellar origins. None are as clear as 3I/ATLAS, but the trend is enough to suggest that interstellar visitors may be more common than previously believed. The universe, it turns out, may be less isolated and more connected than once assumed. One of the most intriguing discussions arises around the possibility of biological material. Some researchers propose that objects like 3I/ATLAS could carry organic compounds formed in other star systems. While no evidence supports that claim directly, the idea forces scientists to reconsider how life-related chemistry might spread across space. If organic molecules exist in interstellar dust, they might survive the long journey between stars. This concept, known as panspermia, gains renewed attention because of discoveries like this one. Others focus on the technological implications. The ability to detect and analyze interstellar objects gives humanity a new observational tool. Future missions could send probes to intercept such objects, collecting samples before they leave the solar system. Several organizations begin developing early concepts for rapid response spacecraft capable of doing exactly that. The idea is straightforward: to be ready the next time an interstellar visitor appears. Science often advances not only through theory but through preparation for unexpected opportunities. Meanwhile, philosophers and social theorists begin exploring the deeper significance of 3I/ATLAS. They argue that every major discovery in science eventually changes how humans define themselves. When Copernicus showed that Earth was not the center of the universe, it transformed human identity. When Darwin proposed that life evolved through natural selection, it changed how humanity saw its origins. Now, interstellar objects challenge humans to rethink their place in the galaxy. The question is no longer only, where do we come from, but also, what else exists out there that we have not yet seen? This question becomes more than scientific. It affects how people imagine the future. If matter can travel across galaxies, could intelligent life do the same? The discovery reignites the long-standing debate about extraterrestrial civilizations. Some scientists remain cautious, insisting that extraordinary claims require extraordinary evidence. Others argue that even the possibility should motivate more research into signals, communication technologies, and advanced observation techniques. The question of what else is out there becomes a driving force for exploration. Within the scientific community, the discussion shifts from what 3I/ATLAS is to what it represents. It becomes a reminder that every observation carries assumptions. Models are built from data, but data is always limited by instruments. What lies beyond current technology remains invisible, not because it does not exist, but because it cannot yet be measured. The realization humbles even the most confident researchers. The more accurately humans study the universe, the clearer it becomes how much remains unknown. Students in science programs begin studying 3I/ATLAS as a case study in uncertainty. It illustrates how science is a living process, constantly refined by new evidence. A textbook might one day describe it as a turning point in cosmic research, not because it revealed everything, but because it reminded humanity that discovery never ends. Each confirmed answer generates more precise questions, leading to the next phase of understanding. In observatories, the remaining data from 3I/ATLAS continues to be analysed for subtle patterns. Researchers use simulations to trace its motion backward, attempting to identify the region of space it came from. Most results remain inconclusive, but even that inconclusiveness has value. It defines the limits of what is currently knowable. Knowing those limits helps scientists refine future methods of observation. Outside science, the event inspires cultural responses. Artists, filmmakers, and educators use 3I/ATLAS as a symbol of curiosity and humility. The public's fascination with space exploration grows stronger. For many people, it represents not just an astronomical event, but a reminder that human understanding is still in its early stages. The object's brief passage through the solar system becomes a metaphor for the fleeting nature of insight, something that appears, teaches, and then disappears beyond view. At the personal level, the story of 3I/ATLAS encourages reflection. Many individuals, even those with no scientific background, feel a renewed sense of curiosity about existence. They realize that science is not a distant or abstract pursuit. It is a direct extension of human desire to know and to connect. The universe becomes less of a background and more of a shared context. Every person, by existing, participates in it. You recognize that this is the real transformation that discovery brings. It does not simply add to the total amount of human knowledge, it changes how humans think about themselves in relation to everything else. The data from 3I/ATLAS will be archived, its numbers stored in databases and papers. But the effect of its discovery continues in the human mind and in the way people question, imagine, and plan. Science thrives on questions. Each time an unexpected object like 3I/ATLAS appears, the scientific process must adapt. Old theories are tested and sometimes replaced by new ones. That adaptation is what keeps knowledge alive. The question that changes everything is not about one comet or one dataset. It is the broader recognition that discovery has no final stage. The universe does not run out of mysteries. As months pass, 3I/ATLAS drifts beyond the range of telescopes. The excitement around its passage begins to fade, replaced by other headlines and new discoveries. But for those who studied it closely, something fundamental has shifted. The sky now looks different, not physically, but conceptually. Every point of light might hide another traveler, another clue, another question waiting to be asked. You conclude that curiosity itself is the engine of progress. 3I/ATLAS may have left the solar system, but its greatest contribution is not material. It is the habit of asking questions that do not end. The universe, by its nature, invites this kind of inquiry. Each discovery opens a door to deeper curiosity, reminding humanity that knowledge is not a destination, but an ongoing dialogue with the unknown. Months pass after 3I/ATLAS. exits the observable range of telescopes. The last images show a faint receding object, its brightness reduced to a few scattered photons. After that, there is only numerical silence, coordinates without light, predictions without confirmation. Astronomers officially mark the end of observation, but the story of 3I/ATLAS does not truly end. Its data remains stored in archives in digital form in research papers and in the minds of those who studied it. Every recorded object in astronomy eventually becomes just that: data. Stars that once shone brightly fade into catalogue entries, galaxies become coordinates, and comets turn into orbital lines on charts. 3I/ATLAS joins this quiet collection. Yet, it occupies a special place because it came from beyond the solar system. It is a reminder that the universe contains travelers that will never return, objects that appear once and then continue endlessly into the dark. Scientists continue to run simulations of its motion. They use gravitational models to estimate where it might be now, many billions of kilometers away. The object is expected to continue through interstellar space for millions, perhaps billions of years, unaffected by the systems it passes. Occasionally, researchers recheck the data, adjusting for errors or using it as a comparison for new interstellar objects that appear. Though it is gone, it still contributes to science indirectly by being part of the foundation on which future studies are built. In universities, 3I/ATLAS becomes a case study in observation methods. It teaches students about the importance of rapid coordination between observatories, accurate timing, and careful interpretation of incomplete data. The lessons learned help refine the strategies used to track future visitors from outside the solar system. What it leaves behind is not a mystery to solve, but a procedure to improve, a pattern that can be repeated and perfected. Among scientists, one topic continues to attract discussion: the possibility that 3I/ATLAS's irregular motion was not caused by typical outgassing or solar radiation pressure, but by some unknown factor. While there is no solid evidence for anything unusual, the small deviations in trajectory remain unexplained. Some researchers propose new theoretical models involving non-gravitational forces acting on interstellar material. Others suggest that more precise instruments will be required to determine the truth. The debate remains unresolved, but it pushes scientific inquiry forward. Outside the research world, the public's interest gradually fades. Space news cycles move quickly, and attention shifts to new discoveries. Yet for a few people who followed 3I/ATLAS closely, its story continues to hold personal significance. Amateur astronomers rewatch old observation footage. Students use it as a topic for projects about interstellar exploration. The event becomes a quiet symbol of how human curiosity can reach far beyond immediate experience, even if no one witnesses the result. For those who work directly on the discovery, the aftermath feels both complete and incomplete. They know they have done all they could with the data. The telescopes cannot follow it any farther. No new information will come from it. Yet they also feel a strange connection to something that now exists entirely beyond human reach. It represents the boundary between what science can measure and what it must imagine. The scientists move on to other work, but 3I/ATLAS remains in the background of their thoughts, a reminder that every discovery is temporary, yet every mystery continues. Philosophers who write about the event describe it as an example of scientific impermanence. They note that human understanding always expands in steps, each new discovery briefly illuminating part of the unknown before the darkness returns. The journey of 3I/ATLAS illustrates that pattern clearly. Humanity learned much from it, its speed, its composition, its probable path, but the ultimate details of its origin and destination remain unanswerable. This incompleteness is not failure. It is an accurate reflection of the scale of the cosmos. Some researchers suggest that future missions could be prepared to intercept the next interstellar object. Space agencies begin early planning for rapid launch systems that could send probes to gather direct samples before such objects leave the solar system again. These discussions mark a practical legacy of 3I/ATLAS. Even if this one has left, the knowledge it inspired may help humanity be ready the next time. The object's departure also prompts reflection on the limits of human perception. Telescopes, no matter how advanced, can only see a fraction of what exists. There may be countless objects like 3I/ATLAS crossing through the galaxy, unseen and undetected. The absence of evidence does not imply emptiness, it only shows how narrow the current field of observation is. In this sense, the universe is filled with unseen motion, a constant background of matter drifting silently between stars. As the data becomes older, the memory of the event settles into history. It joins the record of human efforts to understand the cosmos, alongside the first telescopic observations of planets, the discovery of exoplanets, and the detection of gravitational waves. Each event represents a small extension of perception, a moment when the invisible becomes visible for a short time. Then the moment passes, and the unknown grows again. In lectures and documentaries, scientists often emphasize the philosophical meaning of discoveries like 3I/ATLAS. They explain that astronomy is not only about collecting information, but about recognizing humanity's position within a much larger system. The object's journey shows that most of the universe operates without reference to human presence. Planets orbit, stars die, and matter travels across light years whether or not anyone observes it. To understand the universe is also to accept that it does not depend on us. This realization does not diminish curiosity. Instead, it deepens it. Knowing that the cosmos continues without human involvement gives each discovery a sense of humility. It reminds scientists that their work is not to control the universe, but to understand its laws, however briefly they can. Every dataset, every photograph, every light curve is a conversation with something that exists independently of the observer. Over time, the idea that the journey continues without us becomes a phrase repeated in academic and popular contexts. It captures the essence of astronomy, a discipline that studies things that existed long before human life and will persist long after. The phrase also applies to knowledge itself. Each generation of scientists builds upon the work of those before, but the search for understanding continues beyond individual lives. In practical terms, 3I/ATLAS will eventually fade completely from detection. Radiation, collisions, and cosmic dust will alter its structure over millions of years. It will never return to the solar system. Somewhere in interstellar space it will remain, a small remnant of matter traveling through the void. Yet its scientific and symbolic impact will endure through the data it left behind and the questions it raised. For you, this realization has a grounding effect. It shows that not everything needs to be witnessed to be real. The universe is full of silent continuations, processes and motions that happen whether or not anyone observes them. 3I/ATLAS represents that principle clearly. Its journey is invisible now, but it continues in the laws of motion, in the equations that describe gravity, and in the minds of those who still think about what lies beyond visibility. Eventually, discussion about 3I/ATLAS shifts entirely to academic reference. It becomes part of the scientific record, cited, analysed, and occasionally rediscovered by new generations of researchers. Its influence continues quietly, much like its passage through space. The journey that began with its detection now continues in thought, in research, and in every new question it inspired. The universe moves on. So does human understanding. But somewhere, far beyond the reach of any instrument, 3I/ATLAS still travels, indifferent to the eyes that once watched it. Its path, though unobserved, remains real, an unending reminder that discovery is not possession and knowledge is not control. What begins as observation always ends as imagination, carried forward by the next search for meaning that will follow. After 3I/ATLAS disappears from all detection systems, astronomers begin the long process of organizing the collected data. The task is extensive: thousands of images, measurements of brightness, variations in trajectory, and chemical readings from spectral analysis. Each dataset is reviewed, verified, and uploaded into international databases. The goal is to make the information permanent, accessible to future generations of scientists who may develop better tools to interpret it. This phase marks the transition of the event from discovery to documentation, a common pattern in modern science. As the research continues, one clear observation emerges: 3I/ATLAS changed how the scientists think about the solar system. Before its arrival, only a few interstellar objects had ever been recorded. Its study expanded the discussion about how material travels between star systems. Astronomers now understand that the solar system is not isolated. Instead, it is part of a continuous exchange of matter occurring throughout the galaxy. Every object like 3I/ATLAS is physical evidence that star systems interact more frequently than previously assumed. The findings from 3I/ATLAS also affect how scientists approach future observations. The event highlights the importance of international coordination and real-time data sharing. When the object was first detected, multiple observatories across the world had to communicate within hours to collect sufficient data before it left the range of view. This process demonstrated that science is no longer an individual effort, but a collaborative one, dependent on shared access to information and technology. In the months following the observation, research papers begin appearing in academic journals. They cover its chemical composition, trajectory, and potential origin. Most conclude that it was likely ejected from another solar system during its formation phase, when gravity from larger planets can send smaller bodies into interstellar space. However, some anomalies remain unexplained, including slight variations in its motion that do not align perfectly with current models of non-gravitational acceleration. These unresolved questions keep interest alive and ensure continued examination of the data. Outside academic circles, the story of 3I/ATLAS captures public attention. News outlets report it as a rare cosmic visitor. Documentaries are produced, and educational programs use the event to teach students about comets, interstellar travel, and observation techniques. For the general public, the object becomes a symbol of how small human observation is compared to the universe. It generates renewed interest in astronomy, especially among younger audiences who see the event as proof that discovery is still possible in an age of advanced technology. Psychologists studying science communication find the reaction interesting. They observe that people are drawn to 3I/ATLAS, not only for scientific reasons but for emotional ones. It represents something unreachable, an object that came and left without any interaction. This produces a sense of humility, a reminder that humans are observers of a vast system, not its center. Researchers later call this emotional effect the cosmic perspective, where understanding the scale of the universe leads to a deeper respect for its complexity rather than fear of its size. Within the scientific community, a secondary discussion begins about the cultural meaning of such discoveries. Historians of science note that every major astronomical event, from Galileo's first telescope to the detection of black holes, has expanded not only knowledge, but also human imagination. 3I/ATLAS continues this pattern. It demonstrates that the drive to explore space is not based purely on utility or technology, but also on the human tendency to seek understanding beyond immediate survival. In this context, wonder becomes a functional part of scientific motivation. At several universities, seminars and conferences explore the philosophical aspects of the event. Scholars discuss whether curiosity itself can be considered a form of intelligence. They argue that the act of questioning the unknown, even when no direct benefit is expected, is what defines the human species. 3I/ATLAS becomes a case study in how simple observation can trigger complex intellectual responses. The object's physical absence contrasts with its intellectual presence. It exists now more as a subject of thought than as a body in space. The data collected from 3I/ATLAS also influences future mission designs. Space agencies begin developing rapid-response spacecraft concepts that can be launched within weeks to intercept the next interstellar object detected. These missions would collect direct samples or high-resolution imagery before the object exits the solar system. Several international collaborations form preliminary plans for such projects. While they may take decades to realize, their foundation traces back to lessons learned from 3I/ATLAS. Thus, the discovery continues to produce practical advancements long after the object's departure. As more time passes, 3I/ATLAS transitions from an active research subject to a historical reference. It joins the timeline of key discoveries that shaped humanity's view of the cosmos, not for its size or brightness, but for what it represented: the intersection of observation, imagination, and scientific precision. Its brief presence in the solar system becomes a reminder that discovery is often temporary, but understanding can be permanent. The data remains, but the object moves on. For scientists who work directly on the project, this period brings reflection. Many describe the experience as a turning point in their careers. The observation process, staying awake through nights of data collection, managing equipment, and coordinating internationally, reminded them why they entered astronomy in the first place. It reconnected them with the curiosity that often becomes obscured by the daily structure of research and publication. In interviews, several astronomers expressed that 3I/ATLAS helped them recover their original sense of wonder about the universe. Educational institutions also integrate the case into their curriculum. In astrophysics and planetary science courses, students analyze real datasets from the event. This provides an opportunity to learn not just theoretical concepts, but the challenges of dealing with incomplete or uncertain information. Teachers emphasize that science rarely deals in absolutes. That much of discovery involves managing ambiguity and accepting that some questions remain open indefinitely. 3I/ATLAS becomes a lesson in both the power and the limits of observation. Sociologists examining the event's impact and notice another trend: the connection between wonder and collective progress. The global response to 3/ATLAS, collaboration, excitement, and curiosity, demonstrates how shared fascination can unify people across cultures. Unlike many modern scientific subjects that are tied to competition or politics, this discovery was purely observational and carried no direct economic benefit. Yet it inspired cooperation on a global scale. This reinforces the idea that science functions as both a method of inquiry and a shared cultural language. Over time, discussions about 3I/ATLAS shift from technical analysis to reflection on what drives discovery itself. Scientists acknowledge that while data and equations explain how things happen, they do not always explain why humans choose to seek those explanations in the first place. The answer, many conclude, lies in the emotion that precedes science, the sense of wonder. It is the first step in every investigation, the reason people build telescopes, launch probes, and stare into the unknown. Without that emotional foundation, scientific progress would stall. From this understanding emerges a broader conclusion: the origin of wonder is not external but internal. It does not depend on objects like 3I/ATLAS, but on the human capacity to recognize significance in what is observed. The comet-like body is only a trigger. The real transformation happens within the observer. In this sense, 3I/ATLAS serves as both a scientific event and a psychological mirror. It reveals that the drive to explore the universe reflects the deeper drive to understand existence itself. Years later, when the event is mentioned in textbooks and lectures, it is remembered as much for what it inspired as for what it revealed. It marked a period when humanity's tools reached far enough to glimpse something truly alien, yet familiar in its motion. His legacy continues in every new observation of interstellar matter, every discussion about humanity's role in the cosmos, and every question that begins with "what if?". In the end, 3I/ATLAS becomes more than a passing object. It becomes a symbol of perspective, that even temporary discoveries can change permanent understanding. The study of its brief visit leads to new technology, new methods, and new thoughts. It proves that the most important part of discovery is not possession of knowledge, but participation in the ongoing process of learning. The scientists move on to new projects, the data becomes archived, and new generations of students grow up hearing about the event as history. Yet in the background of all this progress, the same feeling remains: a quiet recognition that the desire to know is endless. 3I/ATLAS is gone, but the sense of wonder it evoked continues to shape how humanity looks outward. In every future discovery, some trace of that same feeling will return. The realization that knowing more about the universe is also knowing more about ourselves.